Cloud, there we go. Welcome. So understanding space through a cybersecurity lens. I'm Jerry Sellers. And a little bit about me. So I did 20 years in the Air Force, mainly space stuff. I worked space shuttle mission control back in the day. I worked about 14 different shuttle flights, including on console for the Challenger accident, and then worked returned to flight after that. So if you saw the movie Apollo 13, anybody, I actually worked for Gene Kranz back in the day. Then did a bunch of other stuff in the Air Force, all space related. I retired from the Air Force in 2004, and then I've been with our small company, TSTI. We do training and workforce development and system engineering consulting, kind of all over the industry. So I'm also adjunct at Stevens Institute of Technology and at Georgetown, do some graduate courses with them. And I'm an Agile guy, so I teach Agile around the industry a bit too. I'm here today with two other folks helping me out, so I'll turn first over to Terry. Terry, if you want to say a few words about yourself.
Hi there, I am Terry Johnson, and I am the chair of the Computer Networking and Cyber Department at Pikes Peak Community College, located here in Colorado Springs. I started in IT over 20 years ago, really specializing in computer networking and then securing those computer networks. Starting out with like Deloitte and Anderson, two of the big five or whatever they're called now, tax and audit firms. And then I realized that I really have this love for education and have served on as both faculty and staff in K-12 and higher ed. Like when I have free time, I really like to spend it on beaches.
So you're, I'm coming to you from Colorado, and actually all of us are in Colorado. So she's at a virtual beach back there. But yeah. And then helped today too by Jason. And Jason, you want to say a quick word about yourself?
Yes, I am a high school student. I'm interested in computer science and cybersecurity. I am on the robotics team, and I've participated in a number of local coding competitions, and I'm just going to be helping out here.
So he's getting a little experience rubbing shoulders virtually with folks in the cyber community. So this is good practice for him today. So our company is TSTI, so we do training consulting around the industry. We like to say we have a front row seat to the industry. We get to see what kind of challenges everybody has at NASA, ESA, DoD industry. We work on support a lot of textbook development work, and our company does on-site training back when you could do that. We've kind of pivoted to 100% virtual training since COVID. We also do coaching and integrated programs, and then we do other consulting, especially in model-based system engineering is a very growing area for us. So I saw one question in there in the chat about reusable rockets. Let's hold that question. That's a good one to bring up when we get to the break. So if you got specific questions about the material, I'll probably handle it right then. If it's a good question, but I think it might deserve a deeper answer, I might wait until the break. So that, if you're okay with that, that's how we'll proceed. So here's our overview of what we're going to try to do this afternoon. We're going to start with big picture. We want to know the context for space. And that context is also the context at which cybersecurity has to occur with respect to space. So we'll tackle that, and we'll look at this thing we call the space mission architecture and how all the puzzle pieces that have to go together to make a space mission be successful. We'll then look at various opportunities. So opportunities for people to do necessarily possibly nefarious things. And with respect to that, we'll look at orbital mechanics and mission operations. So we'll focus on those two, if you will, threat surfaces. And then we'll look at specific threats having to do with the natural environment of space and the man-made environment. And we're going to see the natural environment is pretty darn nasty. So it's hard enough to work in space, let alone you throw humans on there to trying to do bad things. But we'll try to understand both of those potential threat areas. And then we'll end up this afternoon looking at vulnerabilities. And we'll look at two key vulnerabilities, one being RF links, so the RF systems, radio frequency systems shown there in that cartoon as uplinks, downlinks. These are the pipes that carry the data that we use in missions. And then we'll talk a bit about the space data architectures that we use in ground and onboard systems. So here's our objective. Oh, sorry. First of all, this course is based around this textbook. So there's a textbook called Understanding Space, and it's available through that website. This is part of the space technology series. I think there's roughly up to 30 books now in that series that tackle all kinds of different space subjects. So if you're interested in pretty much anything to do in space, there's a textbook probably for it. But this is the introductory book, and a lot of the material here, the images came out of that book. So if you're interested in that, you can try to get a copy of that. So here's our objectives for the afternoon. We're going to start by trying to build some core space knowledge. So we're basically launching you on a trajectory here, where we're going to start by laying the foundation of the launch pad with our core space knowledge. What is the space mission architecture and that kind of thing. And then we'll look at how we build upon that to understand the basic capabilities and trade-offs and limitations as they apply specifically to the cybersecurity domain. We're going to focus on orbital mechanics and the opportunities or lack thereof that creates for getting access to space systems, and then look at the operational architectures as well and see how that can constrain access. Then, as I said, we'll focus on the natural and human-made threats that can be out there, especially the natural ones, and what kind of vulnerabilities that comes out from there as we look at things like radio frequency links and the data architecture. Somebody's asked for the recording. Yeah, I think we'll be posting that recording. I just sent the morning recording off to the organizers, so they're going to put that on Discord somewhere. I don't know where they put that, but if you, did I put my email address? I guess yeah, no, I didn't. Yeah, I put my email address. So if anything comes up in this course or afterwards, please feel free to reach out to me. If you can't find the recording or whatever, I can get it for you. So please feel free to track us down if you need to. So here's our agenda. We're an afternoon session, day one over there on the left. So we're just getting started. And you see the course is broken into kind of half-hour segments. So we'll tackle a subject for about a half an hour. And then I've got some poll questions that I'll ask you, just kind of see if you've been paying attention, and also gives us a chance to discuss some of the topics a little deeper. We'll have time for a little stretch break in there, and also we can tackle any sort of other questions that you might come up with that are a little off topic, but I wanted to build in some time to talk about those somewhat off topic questions. We had some great questions this morning about slingshot trajectories and other stuff. So again, kind of any questions, fair game here. So feel free to come up with stuff, and we've got time built in to do that. So we'll hit each section for roughly about a half hour, take a poll, have a short break, and then we'll get right back at it. And then you want to save up some energy for the very end, because then we're going to have a little cybersecurity challenge for all of you. So I'm going to present you with a scenario, and you're going to have to think through what you do to respond to that potential cybersecurity scenario. So get ready for that. That's coming here at the end of the afternoon. So it should be pretty action-packed, hopefully fun afternoon for you. So let's start with a context. So I'm a big picture guy. I like to think about, okay, how does this, let me show you I can't put together the pieces of the puzzle until you show me the picture on the front of the box. Okay, so this is the picture on the front of the box of what the puzzle is going to look like. And that puzzle has these various key pieces that we want to look at. We put that whole puzzle together, we call it the space mission architecture, which includes orbits and trajectories, spacecraft, launch vehicles, operations, and at the core there, we have the mission itself. So we want to know how all those pieces go together. And that's what we're going to start by tackling. And to do that, we want to first understand, well, why, because we're going to look at the mission, why do we go to space at all? What are the reasons that we would even bother spending all this money, time, effort, risking people's lives to go to space? And space, it turns out, is a pretty big industry. I think as of last year, the latest numbers I saw, space is a $420 billion industry. I mean, it rivals the airline industry in terms of size. So it's a pretty big industry. So where's all this money coming from? Why are people even making money in space? Why do we go to the time and trouble to go to space? So we list here what we call as space imperatives, the unique aspects about space that make us want to go there. And so we have global perspective, clear view of the heavens, free fall environment, resources, and the final frontier. So of those reasons, or those 5 reasons we might go to space, which do you think is the single most important? The reason that we most often go to space, and the reason most people make money in space. Who wants to guess which of those 5 are the most important? Go ahead, you just put it in the chat, or you can shout out.
I'd say the global perspective. You can see the whole world.
Absolutely. Yeah, you nailed it. So I live in Colorado, so I like to tell people the reason we go to space is to get high. That's the main reason we go to space, because it's higher. By being higher, we can see more stuff, right? The more I can see, the better I can understand what's going on. If we could simply build a tall tower and look down, we'd probably prefer to do that, but we can't build a tower quite that tall, although I have some colleagues trying to build a space elevator, but that's another discussion. But by being high, we can see more, right? And the more I can see, the more I can understand what's going on. It turns out back in the 50s, in 1957, when the Russians launched Sputnik, they actually did us a favor. They established the precedent, international law, that you can overfly any country from space. Now, you can't overfly any country in the air. You can't just get in an airplane and go fly over Canada. They wouldn't like that. But you can overfly Canada from space. That's international law. That's an okay thing to do. So that established space is sort of open sky in terms of the ability to go over and overfly anything that's out there. So that was Sputnik 1, and then later on they flew a couple other missions. And then anybody know the first animal to fly in space? The Russians flew the first animal in space. Yeah, it was a dog. The dog was named Laika. Anybody remember Laika? So Laika was a dog that flew in space, and of course we didn't know much about Laika, but, during the Soviet times. But after the fall of the Soviet Union, information came out about Laika, and it turns out Laika was not any ordinary dog. They scoured the entire Soviet Union to find a special dog because they wanted to have a talking dog, because they couldn't have an air-to-ground link, so they needed a talking dog. So Laika was a talking dog. And when Laika came down to land, she was supposed to land on the land, but their early times, their guidance wasn't that accurate. So she ended up landing in the sea. And it was a stormy night, and the little capsule got kind of tossed around. And we finally got the capsule up on the beach, and they opened up the hatch, and Laika came trotting down. They said, "Laika, how was the trip?" And she said, "Rough." So yeah, talking dog, Laika. But so actually that's a lie. Laika couldn't talk. Actually, Laika unfortunately burned up on reentry, which is why the Russians say they invented the hot dog. So anyway, but there we go. But I digress. So we get up there to be high, we get up there to see what's going on. And that's the most important reason. These other reasons are cool too, but in terms of making money, being high is where it's about. So while we're up there, we can do some cool things. So being high, one of the most important things we can do is provide communication. So Arthur Clarke came up with this idea. Arthur, he's a science fiction writer. I came up with this idea in the 40s. Actually, somebody else came up with it, but he's popular for stating it, is that if I could put a satellite that 2 people could see on opposite sides of the Earth, and they can both see the satellite, then we could talk through that satellite. So we can relay information through that satellite. That special orbit we can use to do that is called geostationary orbit. We'll talk about that here in a little while. And if you look at the bottom picture there, you can see this is not quite the scale, the geostationary orbit is pretty popular. There's roughly 400 active satellites up there in geostationary orbit, mostly doing communication. And they're not really stacked up like little BBs there. That's just showing how many are in a given slot. The slots are pretty big. It's about a 1 degree slot, roughly 360 degrees, if you will, around the Earth, in roughly 1 degree slots. So there can be more than one satellite in a slot. But it's a very popular place to be. If you have if you own a slot, if you have license to use a slot, that's literally money in the bank. So it's like owning beachfront property because they're not making any more of it. So very popular place to operate from in space. You can kind of see where the popular places are. You can see there's a lot kind of over Europe. There's a lot over the North America, a lot over Asia, not so much over the middle of the Pacific. So that's where most of the money being made in space today is in geostationary comm. The other big area that's not so much a money maker, although people do make money off GPS, but is certainly an enabler for the global economy, is navigation, and really position, navigation, and timing, global, geospatial navigation services. And of course, the most popular there is GPS, the Global Positioning System, operated by the Air Force, now Space Force. And then, of course, there's GLONASS, there's the Chinese Beidou system, and there's Galileo, the new European system. So there's more and more systems coming available, which is good. It gives us some backup. Because if you think about it, the entire global economy depends on this capability for position, navigation, and timing. If you were to take out that capability, the world economy would be worse shape than it is right now. So really bad. ATMs wouldn't work. It wouldn't be able to use a lot of global communication, and of course, people would get lost. So all of this is key. So it's and the ability to do GPS is provided by the fact that we can put satellites in a high orbit, and standing on Earth, I can see at least 4 satellites at any one time. 4 it turns out to be the magic number I need to solve the problem. So I can see 4 satellites at once. Usually I can see more than that. I can get that by having those satellites up there in a very high orbit. So any place on Earth, you can always see at least 4 satellites. So that's simply an advantage of being up there high. And here on Earth, I can access those satellites quite easily. And now I have the ability to do my navigation. So that high ground, again, that global perspective is being leveraged by GPS and other navigation systems. And of course, the other thing we can do by being up there is we can look down. We can look down and take pictures of what's happening on Earth. So that's what we broadly call remote sensing kind of missions. And of course, obvious one would be something like the nightly weather report. We just had a hurricane pass off the coast of Florida, so you probably saw some of the images from that. All came from satellites. So we have satellites in geostationary orbit and in low Earth orbit that monitor the weather. And then we have all kinds of satellites that do imaging. Planet Labs has a whole number of satellites they do for daily imaging of the Earth. And you can do low resolution, high resolution. Of course, the military does very high resolution imagery, spy satellite type things. We have missions like that do just environmental monitoring that will look for ozone monitoring and things like that. Landsat is a long-term mission that's been flown now for, gosh, going on 40 years, but they've been monitoring the Earth's environment for that long. So nice longitudinal data in terms of behavior. And these spy satellites all go back to the early days. So one of the very first, well, the first military satellite we tried to build was spy satellites. And that was a mission called Corona, not to be confused with the beer or the virus, but the Corona mission was stood up by the National Reconnaissance Office at the time. That was its job, was to go do that. And to give you an idea of the priority, their 13th flight was successful. They had 12 consecutive failures and still got funding to keep going. And they launched these satellites up into space. This is now the early 60s. How did they get the pictures down? Anybody know how they got the pictures down?
Radio wave?
What's
Or
that?
no, wouldn't they drop like film rolls down
Yes.
and go land?
Yes. They ejected the film rolls from the satellite. The film rolls entered they had containers, obviously, entered the atmosphere, and then they popped a parachute, and then they would snatch them out of the air, and then they would send them to a place called Photomat, and you'd get your pictures back in a couple of weeks, right? That was the Instagram of the day, right? That's when we used this stuff called film. Yeah, hard to believe that they actually literally launched rolls of film and then parachuted the rolls of film down from outer space. I mean, it's hard to imagine, but that's what they did. It wasn't until the 70s that they went to all digital. So, I mean, you can pretty much, thank spy satellites for the digital camera capability you have on your cell phone today. The ability to develop the CCDs and that sort of technology came and was pushed by remote sensing kind of missions. So again, why can we do this? Because we're above the Earth, because we're high, because we can see what's going on. So let's explore that architecture now a little bit deeper, now that we understand why we're going to space. And the first part of our architecture is the mission, right? And so in 1961, President Kennedy gave a very famous speech about going to the moon.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
So in that case, Kennedy outlined a very simple mission, right? And at least simple in terms of articulating it, right? Land a man on the moon, return him safely to the Earth, end of the decade. Three goals and objectives right there. So what we want to know about any mission is, first of all, what need are we addressing? Here it was the need to, beat the Russians. But then what are the goals and objectives we're trying to accomplish? And how do we plan to go about accomplishing that? We call that the concept of operations. So we want to know all those things to give us an idea of the why. Once we know the why, we can figure out the how. And the how usually starts with a spacecraft. So a spacecraft is a satellite in orbit, and we'll talk about orbits a bit later here. And that satellite's going to do a job. And that satellite we can break into two parts. We call it the payload and the bus. So the payload is the part that's doing the mission. It's taking the pictures, it's sending it's relaying the HBO signal, whatever it is its mission is doing. And then the bus is there to support the payload. So just like our little cartoon in the bottom there, the school bus's job is to get the payload, the kids, to school. So that payload, we got a live mic there. That payload then is getting transported by the bus, and so the bus has to have what? It has to have structure, has to have propulsion, and it has to have a radio, air conditioning, all the things to keep the payload happy. And that's what we're doing in any mission, right? We have the bus carrying the payload. The payload's doing the mission. The bus is carrying the payload. And we typically sometimes we'll actually split up the operations with that. There's a DoD mission where the Army operates the payload and the Air Force, I guess now Space Force, operates the bus. And that's because it's a big mission and it's a lot to manage. So they split that between two organizations. So, and some science missions may have a dozen different payloads. And so you may have multiple payload operators for different parts of that. So that's kind of how we want to think about our mission. We have our mission at the center, have our spacecraft that's doing the job. We have the payload that's actually doing the interaction, taking the pictures, the bus supporting the payload. And then once we're up there, the spacecraft has to operate from an orbit. And as we're going to see, we can think about an orbit like a big racetrack. And so once I get into that racetrack, I'm going to be going round and around the Earth all day long. And then I'm going to look down. And when I look down, I'm going to see some amount of the Earth. How much I see depends on how high I am, right? The higher I am, the more of the Earth I can see. As I look down, then that cone that you see in that cartoon on the bottom, that cone has a field of regard. The field of regard is everything I potentially can see. And then the field of view is what I actually do see when I say point my camera. I've got an animation of that coming up a little bit later. And then that swath, you see that line across there, that tells you how much of the Earth I can see as I'm kind of going around the Earth. So that swath, think about mowing a lawn, right? I'm mowing a swath across the Earth, and depending on how high I am and depending on some other factors of my mission, that'll tell you how wide a swath I can cut. And if I cut a wide swath, then maybe I don't need to orbit the Earth very many times to see everything. If I have a narrow swath, I may have to orbit the Earth quite a few times before I see everything. And so that's going to be a big trade-off for us in terms of access to information on the ground and access from the ground to the satellite, as we're going to see. We'll look at a thing called ground tracks and see why that's important. The other piece of the problem is getting to space. So here's our launch of the Atlas V launch of the NASA OSIRIS-REx mission from a couple of years ago. So you got a big old Atlas V rocket and liquid oxygen, kerosene engines on the first stage there, RD-180 engines. And that's going to take you into orbit, into that orbit we just talked about. Rockets are broken into stages, and that's because of the just inherent limitations of the rocket technology we have today. In this case, their stage is not recoverable. If I'd shown you a Falcon 9, it should probably show you recovering that first stage. It's also LOX kerosene, it turns out. But that's how I'm going to get to orbit. And we're going to see how much energy that launch vehicle has to deliver for me to get into orbit. Turns out that's quite a bit. Once I'm up there, now I can start doing my mission. And the main reason I'm going to space, I'm up there, I'm high, I'm looking down at the Earth, I'm up there either creating data or moving data, right? So the whole name of the game in the space business is about ones and zeros going from one point to another, right? How those ones and zeros get around are on all these links that we're going to talk about. So that's that communication architecture we show there at the top. So all of mission operations is about people, processes, and things for doing the job. So we've got a lot of things, a lot of infrastructure, manufacturing, launch capabilities, communication networks, and then I have all the people, the mission management and operations that are actually running the mission. So I have a classic picture down there at the bottom. That's the Apollo 13 mission after they successfully got the astronauts back from their harrowing experience. You see, dozens of people there just in the front room, but a large mission like human space flight, International Space Station, literally has thousands of people around the world supporting that. Now, if I have a little CubeSat mission, maybe I only have a dozen or so people supporting that, but still you've got people, right? People, processes, and things that we need to run the mission. Then finally, we have system engineering and project management to pull it all together. So system engineering is our process of turning a need into a capability. System engineering is about balancing cost, schedule, performance, along with risk to deliver our mission successfully. And then we have our project management to lead the team and ultimately try to deliver the program on cost, on schedule, on budget with acceptable risk. And then supporting all that, and especially as we kind of emerge into this area of cyberspace and cybersecurity for space, is we have an organization that we can call out here called the Information Sharing and Analysis Center, the ISAC, started just a year or so ago, to look at trying to pull together some of these threats and opportunities in cyberspace. So they work with industry and they work with government, focusing on three key areas of supply chain, safety, business systems, and overall missions to try to make sure that keep the community aware of what the cybersecurity issues could be. So there's our big picture context. I wanted to understand why we go to space for that global perspective, what kinds of missions we do up there, especially communication, remote sensing, and navigation. When you want to understand what we mean by that space mission architecture, that includes the mission itself, the spacecraft, the orbit, the launch vehicle, the mission operations systems as well. So from a cybersecurity standpoint, what we'd like you to take away here is an understanding and appreciation for how important space is to the global economy. Not only is it a big industry just by itself at nearly $500 billion, but it's integral to pretty much everything. So from cell phones to power grids to GPS to commercial transportation and simply knowing where you are and commercial and financial markets, we the world depend on space. And of course, the more you depend on something, the more vulnerable it can potentially be. And that's the vulnerability we want you to be aware of. And that because of that, space is becoming a larger attack vector that we have to focus on. And then finally, just be aware of the Space ISAC and what that collaborative groups like that can help do for us. All right, there was a good question about reusable rockets I want to get to in here in a second. But any specific questions about what we just covered in terms of big picture? See, we ended up with a pretty healthy crowd, so that's great. Any questions that came out from what we covered?
Yeah, I think I have a question. So I am French, so I have a French accent. So I hope you will be able to understand me. The thing is that I have to go on another. So it was really interesting, and thank you so much. And I have to go on another talk. but can I have your email address? Because I would like to ask you some questions, but I need to leave now. So is it possible that you write it in the chat maybe?
Yeah, it was in the slides, but I just put there too.
I didn't. Okay,
Yeah.
well, that's very nice. Thank you so much. And I will need to leave Zoom really soon.
Well,
Thank
we'll be
you.
doing it again tomorrow and Sunday morning. So if you want to drop back, you certainly can.
At what time? Because it was mentioned.
Tomorrow's at 9 and at
Oh,
1:30.
okay. I
And
didn't
then
see.
another one on Sunday at 9 a.m.
Yep.
Okay. It was not written on the.
Yep. And then we have
I'm not sure. Is it written on the DEFCON schedule website with Aerospace Village? I'm not sure. I didn't see it.
It should be. And Matt, Matt should be able to answer that.
Yep,
But
it
it's
is.
all there.
And if you check in the Discord, there's a Understanding Space Discord channel. Schedules in there as well.
Okay. That's
Excellent.
great. Thank you.
You bet. Any other specific questions from what we covered? All right, I'm going to give you the poll. So let's launch the poll there. So take a couple of minutes to answer the poll, and we will start back up in about 10 minutes. So this gives you a chance to answer the poll, and then we'll cover the poll, and then we'll pick right back up there, and we're going to hit opportunities. So buckle up. We're going to talk about orbital mechanics when we get back. So go ahead and take the poll, take a stretch break if you need it, and then we'll dive into orbital mechanics here in a minute. And do your best with the poll questions. And then if there's any other questions you have from what we've covered so far, or if there's something you want to make sure I do cover, please put that in the chat. All right, we're getting pretty good participation in the chat there, or in the poll. Give everybody another minute or two, and then we'll go through the poll and see if we have any other questions, and then we'll pick up from there. All right, let's see how we did. I'll in the poll here and share the results. So, all right. So, single most important reason we go to space is to get high, right? Ultimate high ground, to get that global perspective. It's more than just getting above the atmosphere. In fact, we'll see we don't always even get above the atmosphere completely. It's about getting up there so we can see more stuff. That's the single most important reason. And it's not to experience zero G. So we will talk about that word. We don't like to use that word. So the part of the spacecraft that does the business, basically does the mission, we call that the payload, the thing that takes the pictures or collects science or whatever. And then mission operations systems is all the ground and space-based infrastructure we need to coordinate. We call that the glue that holds the mission together. So that's broadly, we call that mission operations systems. Space capabilities, yep, definitely true. It'll become so integral to everything we do. It's hard to imagine life without space. We've become, if anything, too dependent on it. And then ISAC focuses on those key areas there, supply chain, business systems, and missions. So good stuff. Any questions before we dive a bit into orbital mechanics? Right. So when we're done here, the goal is to make you all genuine, bona fide, certified orbital mechanics. So, and I can tell you where to buy the toolkit, but you'll be an orbital mechanic. You'll be certified to fix people's orbits. You'll be all ready to go. So that's what we're gonna do in this section, is really focus on opportunities. So where are the opportunities to actually do things to space systems? And some of those are quite limited, as we'll see, based on things like orbital mechanics. Some of them are quite open because we have a pretty wide attack space potentially in the area of mission operations. So we're going to look at orbits and operations as two opportunity areas that we have to focus on. So as I said a little bit ago, that when we look at orbits, to first order, you can imagine an orbit is like a big racetrack. So think of this racetrack going around the Earth, round and round all day. I've got the Hubble Space Telescope in that racetrack, and it's just going around and around all day long. In the US, we have a kind of a popular sport called NASCAR. And the joke is, if you know, how do you escape if a NASCAR person is chasing you? And the answer is turn right. Because in NASCAR, they just turn left all day long, going around the track. And that's pretty much what a satellite does. It just goes around the track all day long. In low Earth orbit, that takes it about 90 minutes to go once around the Earth. So it's roughly 15 times a day. It's going to go around the Earth. And that's what it does. And that's what we want it to do. We want it to be predictable. We want it to be in the same orbit all the time. And those are things that they're going to help us understand how to do our mission operations. So we're trying to get into that racetrack. Well, how do we get into that racetrack? Well, to get into that racetrack, we have to remember there's this thing called gravity. And so if you drop something, it goes down. And if you forget how gravity works, just remember the Earth sucks. It just pulls it down. So if I drop a baseball, it's going to fall. So in my cartoon in the upper right, I now have two baseball players. I have one who's going to drop a ball, and I have one who's going to throw a ball from the same height at the same time. So if I drop a ball and I throw a ball, which one should hit first? Well, way back in the day, there was a guy named Aristotle, and he thought that if you had a heavy ball and a light ball, that the heavy ball would fall faster. And it wasn't until Galileo came along and said, hey, let's try it. And he figured out, well, wait a minute, heavy ball, light ball, everything falls at the same rate. So it turns out gravity doesn't care about the motion of the ball. You can throw it, you can spin it, you can do whatever you want to it. It's still going to fall at the same rate, which at the surface of the Earth is about 9.8 meters per second squared. So if you don't believe me, got a little video here that shows this simultaneous dropping and throwing. So I'm going to drop a ball here and throw a ball at the same time. And you can see there in slow motion, they're hitting at the same time. If anybody likes the Mythbusters, remember the Mythbusters, they did one where they shot a bullet and they dropped a bullet. So the bullet went like 300 feet and then hit the ground. And they showed the same thing, that whether you drop it or even with a bullet, right, it's still going to fall at the same rate as when you drop. Okay, so what does that mean? Okay, so now we're going to do a little thought experiment here to understand orbits. So picture the Earth, right? Imagine the Earth is a perfect sphere. If the Earth were a perfect sphere, then for every 8 kilometers you go horizontally, the Earth curves away 5 meters. So we're going to do a little thought experiment here. We're going to build a tower on the Earth that's 5 meters tall. And on that tower, we're going to put a diving board that's 8 kilometers long. So if I walk all the way up to the edge of that 8 kilometers and look down, the Earth is going to be 10 meters below me because I started out 5, I went out 8 kilometers, the Earth curved away 5 meters, so now the surface of the Earth will be 10 meters below the edge of the diving board. Okay, well now, imagine I was going to throw a baseball. So I'm going to go back to my tower, I'm going to throw a baseball, I'm going to throw it really fast. I'm going to throw it 8 kilometers per second. So that means it's going to reach the edge of the diving board in a second. Well, how far will it fall in a second? Well, it turns out the distance you fall is 1/2 AT squared. So A is 9.81, so we'll just call that 10, and half of 10 is 5. So basically in 1 second, you're going to fall 5 meters. So you started out 5 meters above the surface, you went out 8 kilometers in a second, you fell 5 meters, and you are still 5 meters above the surface. Well, what's going to happen the next second? Well, you're going to go another 8 kilometers. You're going to fall another 5 meters. The Earth is going to curve away another 5 meters. You're still going to be 5 meters above the surface. You are in a circular orbit. What did it take to get into a circular orbit? You had to go 8 kilometers per second horizontal. Is this a condition of zero gravity? No, you're falling. The Earth is pulling you down. You are just going so fast forward that your Earth is curving away as fast as you go forward. So you keep missing the Earth, right? You're following, but you keep missing the Earth because the Earth keeps curving away from you. That's what allows you to be in a circular orbit. It's about that horizontal velocity. So sometimes people talk about centrifugal force stuff, or if anybody tells you about centrifugal force with respect to orbits, just that's not right. There's no such thing as a centrifugal force, it turns out. It's all about the speed. It's about going fast, and so fast that you keep missing the Earth. If you don't believe me, check Newton. You go into Newton's, if you can see Newton's sketch pad back when he was in his 20s, and he drew little cannonballs being launched from cannons and showed how you would get into orbit, right? And there was no centrifugal force concept going on there. It's just about the velocity and this concept of gravity. So depending then on how hard I throw the ball, I'm going to get into a different orbit. So at any given altitude, there's only one specific velocity that'll give me exactly a circular orbit. If I throw it a little faster than that circular orbital velocity, then I'll be in an elliptical orbit. If I throw it slower, then I'll become an intercontinental ballistic baseball, and I'll take out Rio down there. The shape of this trajectory is actually also an ellipse. Now, they might have told you in high school physics, and you throw basketballs or baseballs or something, that those were parabolic. They're not. It's an ellipse. So this is an ellipse that happens to intersect the Earth. If I do, in fact, throw the ball really, really fast, then I can enter my own independent orbit around the sun. That's different. I'm no longer tied to the Earth, and I'm in my own independent orbit around the sun, different than the Earth, but I don't really go anywhere. And I used to say we don't do that, and then we started doing that, and that's, we call that Earth trailing orbits now. So we use that for solar observation. If I want to go somewhere, I got to throw the ball even faster, so it goes out to the edge of the Earth's gravitational sphere of influence and actually has excess velocity to go somewhere. We call that hyperbolic excess velocity. So when NASA launched the Perseverance rover to Mars last week, it not only had to escape the Earth, it had to escape the Earth with extra velocity that would allow it to go all the way to Mars. So it left Earth on a hyperbolic trajectory. It then entered an elliptical trajectory around the sun, and then it's going to encounter Mars again on a hyperbolic trajectory, and they'll have to fire rockets to enter orbit. Well, actually, they're with rover, they're going to directly enter. They got a big heat shield, so they're going to just slam right into the atmosphere. That's how they'll bleed off all that energy, and then they'll land. on Mars using their complicated sky crane thing they have worked out. So no matter what I do, there's only 4 options: circle, ellipse, hyperbola, parabola. And in reality, you can never get a perfect circle and you can never get a perfect parabola. So the only other things we'll see is in reality are ellipses and hyperbolas. And for our business of orbiting around the Earth, everything is an ellipse. Now, a lot of orbits are close enough that we call them circular, but realize you go out enough decimal places, they're not exactly circular. So those are our orbit options. Any questions on that so far? What it takes to get into orbit?
What are there like orders of magnitude in terms of how much power you need to get out there? Does it like increase significantly, or is it all fairly linear?
That's a really interesting question. So let me tackle that here in a second, because that's an interesting way to think about it. So when I'm getting up into orbit, so first of all, I got to launch the ball, right? So I got to get that ball going fast. So if I don't get it going quite fast enough, it's going to smash into the Earth. If I have it going just fast enough, it enters a circular orbit. If I go a little faster, it's going to enter an elliptical orbit. So as I said, right around the Earth, low Earth orbit, a couple hundred kilometers up, we're looking at going about 8 kilometers per second. But when I talked about that racetrack, the bigger the racetrack, the more energy, right? And we're talking about mechanical energy here. The bigger the racetrack, the more energy. So if I want to go higher, I'm going to have to throw the baseball harder, right? So in low Earth orbit, I'm going about 8 kilometers per second. But as I go out to higher orbit, let's say all the way to geostationary orbit, which is 36,000 kilometers away, I'm now only going about 3 kilometers per second. Okay, well, where'd the energy go? Well, it's all potential now, right? I don't have the same kinetic energy. I have more potential energy because it costs me energy to get out there. Right? I have to spend energy to get higher, right? I climb out of that gravity well. But so so I need to get out to geostationary orbit from low Earth orbit costs you about 4 kilometers per second extra delta V to go from low Earth orbit all the way to geostationary. Turns out that's about the same amount as it takes to go to the moon. To go from low Earth orbit to the moon is pi kilometers per second. So it's 3.14 kilometers per second, give or take. And then to get into lunar orbit is about another 800 meters per second. So it's about 4 kilometers per second to go from low Earth orbit to the moon, about the same as geo. And going to Mars is only about 5.5. So it's not exponential, and it's not really linear either. But one of my favorite science fiction writers, Robert Heinlein, once said, low Earth orbit is halfway to everywhere. It costs you about 8 kilometers per second to get into low Earth orbit. If you have another 8 kilometers per second available, you can go anywhere in the solar system eventually, right? It might take you 9 years to get to Pluto, but you'll get there, right? And so it's all about the gravity, So, if you live, there's certain parts of the country and parts of the world, when you ask people how far something is, they tell you in time, not in distance, right? So it's all about how you think about it. So in space, the distance is not so important. It's about the energy, right? And we'll use that delta V as our kind of coin of the realm there. So that delta V then is, depends on the orbit. And then, so the low Earth orbit is about 8 kilometers per second, as I said. If you go higher, this number goes down. This goes down to about 3 kilometers per second out at geo. So it's all about trading the energy, though. This is the conservation of mechanical energy. So just like being on a swing, right? So when you're going low, you're fast, and when you're going high, you're slow. So I'm trading kinetic energy for potential energy here, right? So at the high point of the orbit, which we call apogee, I'm going slowest, and at the low point, we call perigee, I'm going fastest, but my total energy is the same. Energy is conserved. We say energy is a conservative field, which means whatever energy you start with, you end up with, which is nice because that means if I tell you the energy of the orbit of the satellite at any one spot, I know it at every spot. So I don't have to continuously track stuff in orbit. And I really probably couldn't do that even though I wanted to in a lot of cases, which is good news because that means I only have to track it for a little bit, and it's gonna, if I know that energy is gonna be the same all the time. So that's a big advantage for that. The other thing that's conserved in my orbit is angular momentum. So angular momentum is a vector quantity. So if you wrap your right hand around the direction of the orbit, it'll tell you the angular momentum vector. So you can see that in this animation. So that what that means is that orbit plane is fixed in space. So the Earth is rotating underneath me, but that plane is fixed with respect to the stars. Right? So you see that angular momentum vector, that big arrow pointing out there. That's a orthogonal to that orbit plane. But the plane itself is fixed in space, right? And the Earth is rotating underneath me. And that's a key thing to try to visualize, because most people, it's hard to imagine something being fixed in space, but that's because of angular conservation of angular momentum. And that's important in terms of what I can see when I'm going around. So as I'm going around, this is animation. This is not an artist's conception. This is using an animation, a simulation tool called System Toolkit, made by a company called Analytical Graphics. We're an educational partner, so that's my advertising for those guys. But they make a neat tool, and that tool helps us understand the behavior here. And the circles you see represent different things that I can look at. So that big circle, that outer circle, represents everything I can see out to the true horizon. And this satellite is in a 700-kilometer orbit. The littler circle represents a field of regard for what we call an elevation angle of about 60 degrees. That big circle is an elevation angle of 0 degrees, basically looking along the horizon. As I go up to about 60 degrees, I get this circle. And then when I look down with my camera, you see that little itty bitty soda straw. That's what I can actually image with my high resolution camera. Typically, these high resolution imagers only have about a degree or so field of view. That means it's going to take me a long time to image the whole Earth. So that swath then is telling me how much of the Earth I'm covering on a given pass. And it's also going to tell me when I can see the satellite and when the satellite can see me. Right? These are the opportunities I have to interact with that satellite. So as that satellite's going over, imagine that we're tracing a line on the Earth, right? So it's just, we're going to call this the ground track. So as I'm going around the Earth, the yellow there is the equatorial plane, just for reference. As I'm going around the Earth, so notice that the satellite stays in its plane and the Earth is rotating underneath that plane, which means I'm basically doing like a spiral cut, if you will, of the Earth as I'm going around. And so if I'm on the ground and I want to see that satellite, I have to wait for it to pass over me, or think about another way, me to rotate underneath its orbit plane, right? Depends on how you want to think about it. And that creates our ground track. So we have a static map, because it's hard to move a map. So we just have a map, and we have our guy standing down there in South America. So when the satellite crosses the equator on its first orbit, let's say, the person could look over and see the satellite to his east. Now, imagine it's a low Earth orbit satellite, has a period of about 90 minutes. Now, the Earth is going to rotate 22.5 degrees in 90 minutes, 15 degrees an hour. That means the next time the satellite passes the equator, from the person's standpoint, the satellite will now be to his west, okay? So the satellite stayed in the same plane, the Earth rotated underneath the orbit plane, right? So, and probably the next orbit, on the third orbit, it'll be beyond the horizon, and you won't even be able to see it, right? So this is telling us when I can access that satellite to have it take pictures of me, have me talk to it, or if I was trying to do something to it, when I could even have that opportunity. So then different orbits will have different ground tracks. So there's things that we can adjust on the orbit. We call their orbital elements. And one of those is the size of the orbit. And the bigger the orbit, the longer the period, the longer it takes to go once around the orbit. So here you see different orbits, A, B, C, D, E. And notice A has a period of 2.7 hours, B has a period of 8 hours, C has a period of 18 hours, and E has a period of about 24 hours. Notice what's happening to the ground track. The ground track is getting scrunched together. That's our technical term, scrunched. We're getting scrunched together until I get to orbit D, which ends up being a figure 8. So orbit D, the period is about 24 hours. So we say it is synchronized with the Earth's rotation. In other words, it is geosynchronous. Now, A, B, C, D, A, B, C, and D have the same inclination. So inclination is the angle of the orbit with respect to the equator, if you want to think of it that way. So if I was orbiting around the equator, we'd say we have an inclination of 0. If I was orbiting around the poles, we'd say you have an inclination of 90. And in the case of A, B, C, and D, they all have an inclination of 50. And I can tell that by looking at the highest point, the highest latitude that it reaches. So you see where the high latitude is 50 north, 50 south. So that's telling me the inclination is about 50 degrees. And then look what happens to orbit E. Now I shrink the inclination, so it's now is going around the equator. And so now the ground track for orbit E is a dot on the equator. So it is now stationary with respect to that spot. So we call it geostationary. It is orbiting, it's going 3 kilometers per second, but it's orbiting at the same rate that the Earth rotates. So that gives me that perception of it being, you know, always over the same spot. It is. It's orbiting exactly the same rate at which the Earth is rotating, which is why it seems to hover over that same spot. But it's going 3 kilometers per second. It's not hovering by any means. So those different ground tracks give me different opportunities to access the different orbits. So here's an example. This is the actual International Space Station. You can see it going around in orbit. Its ground track. And so you can see the trace it makes on the globe and then the ground track. So it has an inclination of 51.6 degrees. That's because they had to launch pieces of it out of Russia. And the lowest inclination Russia could reach was 51.6 because they launched from Baikonur in Kazakhstan. Would have been easier for us if it had been launched everything from Florida, but that's another story. So that's our ground track. This is the International Space Station. This is what oh, go ahead.
Can I ask a question about that? So
Sure.
you said, is it because you're closer to the equator, you get more spin from the Earth? Is that why Florida is better than Russia?
Yes, that's a short answer. So when we're launching everything from the shuttle, if we were to launch due east from Florida, we get maximum effect of the Earth's rotation. But because we had to launch from Florida into 51 degrees, which means we had to go somewhat northeast, we lost capability. And they ended up having to completely redesign the external tank of the shuttle to remove 8,000 pounds of weight so that they could get the stuff into orbit. It's quite a heroic tale we could go into offline, but it all came, it's amazing. And, you know, so politics drove orbital mechanics, which drove technology. It was pretty amazing. But that's the way the world works some ways, sometimes. But yeah, great question. So here's our geostationary satellites. So what you'll notice here, a couple of things. First of all, one geostationary satellite cannot see the entire Earth. In fact, to cover the entire equator, you need 3 satellites, and then you get overlapping coverage. But a geostationary satellite can only see up to about 70 or 80 degrees latitude. So you end up with this triangle on the North Pole and the South Pole that a satellite from GEO cannot see. Or said another way, if I'm on the North Pole, I can't talk to a satellite in geostationary orbit. So if you have a DirecTV dish and you're planning to move to the North Pole to visit Santa Claus, don't take your TV dish with you. I don't know what Santa Claus does, but he cannot get DirecTV. So for the most part, we don't care because there's not that many, nobody lives up there anyway. However, there are military missions that do care, and then we'll use a different orbit called a Molniya orbit or highly elliptical orbit that can cover those high latitude regions. But I didn't include an example of that. But if you want to talk about that, we can. So quick overview then. This is our orbital mechanics. There's how we calculate some of those things. I had to put in a second order nonlinear vector differential equation just to see if anybody was paying attention. But a little bit here of how we solve that equation. We can talk about in more detail if you want in the break. But I want to get to operations and then we'll pull up our poll. So remember, we have these things called mission operation systems, which are all the people, processes, and things we need to do missions. So we have manufacturing, launch, and things like our mission control center, which you're used to seeing on TV. And then we have our communication architectures which are all those links that move the data around. Remember I said space is all about moving the data. So I have ground stations and control centers, and I have relay satellites. All that's happening to help me move the data. And I have various methods of doing that. So there are various networks for helping move that data. So on the top, we see the Air Force Satellite Control Network, which I guess could now be called the Space Force Satellite Control Network. I'll never be able to say that. It has sites all around the world they use for talking to satellites. They do, they talk to what, about 450 different satellites a day, if I recall. That's the Air Force network. There's a Navy network, there's an Army network, there are commercial networks. There's a commercial network called Universal Space Network, and they have sites all over the world that you can rent basically by the minute to talk to your satellite. Then NASA has a deep space network. You see there on the bottom. They have 3 sites in California, Madrid, and Australia. And then NASA has something called the Tracking and Data Relay Satellite Systems, which are satellites in geostationary orbit that are used to talk to satellites in low Earth orbit. So if you see video coming from the International Space Station, it's probably coming through TDRS. So that's how they relay data. So all of that represents really critical infrastructure. Without those, you can't run your mission. You got to have those to talk to your satellite, and your satellite to talk to you. So those are important parts of the problem here. And then we have various operational activities we have to accomplish. So there's 9 different activities shown in this cartoon. The one you probably most used to thinking about is flight control. You see on the upper right there, you see people sitting at a console, with a headset on, managing the mission. But that's really just the tip of the iceberg, right? You have people doing planning, you have people moving the data, you have people doing tracking, maintenance and support, spacecraft support, mission data archiving, all that, right? All of these are things that happen to make mission operations effective. And a key part of that is that mission data delivery and data processing, right? Because it's all about moving the ones and zeros, and these are expensive ones and zeros, right? I'm collecting data on what's happening on Mars. That's cost me a lot of money to get that data. So I want to get that data. So I have to have the data generators in space, and then have the data analyzers on the ground. And we need to make sure we have the tools in place to do that. And we have a lot of trade-offs to make in terms of what we do in the operations planning. On one hand, we'd love satellites to just take care of themselves, be 100% autonomous. On the other hand, we maybe have invested $1 billion in that satellite. We don't really want it to just go wandering around the solar system on its own, without supervision. So there's a trade between spacecraft autonomy and how many people we have on the ground. And people on the ground are expensive. For every person you have sitting in a seat on a console, you probably had to hire 5 people, because by the time you have 3 shifts a day, and then people take vacations and they need training, it adds up. So for long-term missions, more than half your mission cost can be in operations. Was there a question? Okay. And then of course, anomaly response, right? So if I have a CubeSat that I built, university built, and it has a problem, I can get around to fixing it next week and nobody's going to care that much. But if GPS has a problem, I probably need to fix it right now, because we've got, the whole world depending on it. So that and, understanding the state of health and understanding the new hardware and software that I'm flying are all parts of the trade-offs I have to do in mission operations. So here are the key tasks again, just as a review of what we have to do in mission operations, those 9 key tasks and the trade-offs that go with that. And then these are the takeaways from a cybersecurity lens. First of all, getting to space is hard, right? 8 kilometers per second, not easy. Orbital mechanics inherently limits some of the things we can and can't do for space operations, and when you can even get an opportunity to talk to a satellite. And finally, there's a lot of things going on in mission operations, and that creates a fairly large attack surface. Again, people, processes, and things that I can get into, often spread all over the world, that I have to be concerned about. So all of these are important things for us to consider from a cybersecurity and cyberspace lens. I had a question here. Does translation introduce significant orbital effects? What do you mean by translation? Hierpin? I don't know how you say your name there. Can you clarify what you mean by translation in your question? I'll have to come back to that again. So it's in the chat. You say, does translation introduce significant orbital effects? I don't really do that. Oh, no, you're still there. Irpin, if you can, sorry, the Earth's moving around the sun. No. The Earth is, so I'm in orbit around the sun. The fact the Earth is moving around the sun does not create any orbital effects on the orbit itself. Now, the sun can have an impact, gravitational impact on my spacecraft. We call that a gravitational perturbation. The moon as well. So if you see out of geostationary orbit, we have these sun-moon effects that actually impact the spacecraft's ability to stay within the box that's been assigned. And so you have to spend a little bit of energy every year to stay within your box, because if you just leave it alone, the sun and the moon will start to move you outside the box. And we don't want to be outside the box. So we spend a little energy to do that. Matt asked about CubeSats. So a CubeSat was a standard that was invented about 20 years ago by some folks out at Stanford and Cal Poly. These guys, and they're still in business today, I know the guys, they just decided one day that they were going to define a CubeSat to be 10 by 10 by 10 centimeters, right? They just said, okay, so 10's a nice round number in centimeters. And so that became a CubeSat standard, and now, of course, that's a 1U CubeSat, 10 by 10 by 10, and you can make 2U, 3U, 9U. People are doing 26U, at which point U becomes stupid. But the nice thing is what happened, it became kind of a self-licking ice cream cone, in that this became a standard size satellite, for a tiny little satellite, and people then created abilities to launch those. And so now if you want to launch a satellite, there are a number of companies that will launch CubeSats for you, as long as you follow the CubeSat standard, and it's usually 1, 2, or 3U is the most common that you see. And if you stick to that standard, then folks like NanoRacks can get you launched in 6 months, and the cost is getting down to the point that that literally high schools are launching their own satellites. So it makes, of course, now we have this massive proliferation of small satellites, which creates other problems that we'll talk about. But it's really lowered the barrier to entry for a lot of organizations and countries and even schools to build their own satellites. And that's obviously a good and a bad thing, depending on who you ask. Did that answer your question, Matt, on that?
Yeah, it did. How much, you said it was getting cheap. How much does it cost to actually launch one?
Launch, I think last time I checked, for about a 1U, and there's a lot of it depends when it comes to the price tag. It was in the $50,000 to $100,000 range, I want to say.
Huh.
And the CubeSat itself, if you want to build one that'll actually work for more than a day, you're going to end up spending $100,000 probably anyway. So yeah, a couple $100K, you can get a reasonable CubeSat with a payload that actually can do something.
Wow.
Which, from millions to hundreds of thousands is pretty good. And you could, from somebody, you might be able to even do it cheap. That's if you actually wanted to do something. If you just want to build a toy, you can go cheaper than that. But people usually going to go to the trouble, they kind of want it to work. So.
No, it's cool. Thank you. That was perfect.
All right, let's pull up the poll here. Let me launch the poll. While I launch the poll, if anybody has any other questions, you guys had some good ones there. So go ahead and answer the poll, and then if you don't have any other questions, we'll start up in about 5 minutes. So take the poll, take a stretch. And then when we come back, we're going to focus on threats. So we're looking at the natural environment and the human environment in terms of threats. So if you thought you wanted to be an astronaut, be ready to be disappointed. Any questions? Was there a question? All right, so we'll start up again in a minute or two here. All right, getting there with all the poll answers. Just give you another minute or so, and then we'll review that and then start into our next topic. All right, let's see where we ended up. So how fast you need to be going? 8 kilometers per second, not 8,000 kilometers per second. That'd be pretty dang fast. Not the speed of light for sure. The speed of light is how fast you'd have to be going to go into orbit around a black hole. But to orbit the Earth, you only need to go in 8 kilometers per second. Can you see any LEO satellite from any spot on Earth anytime? No, you can't. So again, the key there was low Earth orbit satellite, because that's low is pretty low, as we're going to see. So you can only see it certain times of the day, maybe only a couple of times a day, depending on where you are. A geostationary satellite definitely cannot see every spot on Earth. You can only see about a third or so of the Earth at any given time, not even quite a third. So that means we need multiple geosatellites to provide full coverage. So if a bad guy wants an opportunity to covertly contact your satellite, they're going to have to wait until that satellite passes over them. There's really, now they could, they could bounce something through another ground station anywhere. But if I'm trying to do it directly, I have to wait for it to pass overhead. And then opportunities to threaten space ops, all of the above. Everybody got that. So pretty big threat surface there that we have to concern ourselves with. So good stuff. All right. So who wants to be an astronaut here? Who wants to be an astronaut? What if I could just, you didn't have to go through all the training, I would just get you into space.
Yeah, sounds great.
Oh,
as long as I don't have to pay money.
All right, well, after we go through this section, let's see if that's still the case. All right, so here we're gonna look at threats. We're gonna look at natural threats and man-made threats. As we're gonna see, the natural threats are bad enough. And we don't need to give me human threats, because we got enough to deal with, it turns out. So we want to look at both kinds, though. And the natural threats especially are important, because about a quarter of all anomalies that spacecraft experience are a direct result of the natural environment. So you can read all the different things that have happened over the years to different satellites because of the natural environment. There's a radiation storm that affected the stereo satellites. There was a coronal mass ejection that impacted the Dawn satellite when it was orbiting Ceres. The Galaxy 15 one is interesting because, again, this was having to do with electrostatic discharge that caused because of a solar flare. And that satellite lost its mind. It was wandering around geostationary orbit out of control. So people on the ground could not send it any commands, but it was broadcasting. It was on, and it was broadcasting. So it was interfering both physically and RF to other satellites. Other satellites had to actually get out of the way of it. And then eventually it kind of accidentally pointed away from the sun, and the battery discharged, and it did kind of a Control-Alt-Delete and reset itself, and then it was fine. So that was a crazy one. And then that's animation in the top here. You see an impact of, this is a collision between two satellites. One was a dead satellite, one was a live satellite. And that caused a whole bunch of debris. So these are all just issues that come up because of the space environment. Because space is dangerous. You got a lot to worry about up there. So no beans on the space station. Just keep that in mind. Don't fart in a spacesuit. So where's space? It turns out space is not very far away. It's about 100 kilometers, 60 miles straight up if you could drive straight up. There's something called the Kármán line that kind of defines, a generally accepted beginning of space, but there really is no internationally defined exactly where space begins. In fact, if you were only at 100 kilometers, you couldn't stay in orbit because there's just too much drag. You need to be at least another 20 miles further before you could even have a hope of staying in orbit very long. And really, you want to be even higher than that. So if any of you bought your tickets to ride on Virgin Galactic, I guess it's going to be early next year now, $200,000, you're going to get a ride to space. And they're going to define space as 100 kilometers. So you're not going to go into orbit. You're going to go up and you're going to come down. But hey, $200,000, trillionaires, there you go. So space isn't that far away. So if you imagine the Earth were the size of a peach, the International Space Station is just above the fuzz. Right? So the fuzz represents the atmosphere. It's just that little fuzz, and we're not that high up. I mean, we're like right there. In fact, it's not even to scale in that picture because it's too hard to draw it that close. Really, really, really close. That's to get to space. Now, once I get in space, space is really, really, really big. So to try to put those distances in perspective, we tried to put some things to scale here. So imagine the sun were the size of a house, then the Earth is the size of a baseball, so roughly about 8 centimeters or so in diameter, no, 10 centimeters in diameter. But it's 1.2 kilometers away, or 3/4 of a mile away. That's how far away we are from the sun. And the moon is the size of a large marble, about 1 inch in diameter, and it's 10 feet away or 3 meters away. And this is the one I have trouble wrapping my head around because you look at the moon at night, it seems closer than that. It seems bigger than that, but it's really just optical illusion and how our brain processes stuff. So the moon, get a baseball and a marble out sometime and pace off the distance, and you won't believe it, but it's true. I've reran the numbers many times, and that's how it works out. So, and then you go to Pluto, and Pluto's 20, almost 30 miles away, and again about the size of a marble, 30 miles away from the sun. So just the size of the solar system is a little hard for us to grasp, really. So huge distances involved here. But once I get out to those distances, once I'm out there in space, there's a lot of nasty stuff I have to worry about. So there's 6 main things that we worry about: gravitational environment, the atmosphere or lack thereof, and being in a vacuum, the debris environment, and then radiation and charged particles. So I'm not going to say much about the gravitational environment. That tends to be a bigger issue for fluid handling and especially for humans. But we're going to focus on the things that are the biggest threats to spacecraft, which are all the other things. So let's start with atmosphere, drag, and atomic oxygen. So in low Earth orbit, there's still a little bit of drag, and there's still a little bit of atmosphere that's going to slow me down. So the atmosphere basically is like friction on my spacecraft. It's going to rob energy from my orbit. Now remember I said the bigger the orbit, the more energy. So if I take energy out of the orbit gets smaller. Right? Orbit getting smaller, eventually it gets so small that I re-enter the atmosphere completely. That atmosphere decreases exponentially with altitude. So come visit us here in Colorado and get off the plane, and you'll know immediately that the atmosphere has decreased a bit from sea level. The atmosphere doesn't go completely away ever. Well, not ever, but I mean, goes up to, NASA detected molecules of the atmosphere up to about out by the moon, but those are like molecules they detected. But in terms of low Earth orbit, we use 600 kilometers as kind of a rough rule of thumb. So in other words, if we're below about 600 kilometers, then atmosphere drag is something we probably have to worry about. If we're above 600, then probably it's nothing we need to worry about. But again, it's not hard and fast, it's just roughly. Because when I look at that drag equation there on the left, the drag that I get from a satellite depends on a number of things. One of the things it depends on is the velocity, how fast I'm going, the drag coefficient, basically the shape, and then the cross-sectional area of the spacecraft. So I know most of those things. What I don't know very well is the density, because that density of the atmosphere changes day and night. It changes with season, it changes with latitude, And it changes based on what mood the sun happens to be in. And the sun goes through these 11-year cycles of moods, at least as long as we've been watching it, which isn't that long really. But so far it's 11 years as far as we can tell. And we're actually just coming off the latest solar minimum. So the sun is always putting out these charged particles I'm going to talk about, and we call the solar wind. So these charged particles are always coming out from the sun. And think of that as a constant breeze coming from the sun. But the sun is going to get more active, less active over this 11-year cycle. Right now, we're just coming off the solar min, about ready to start back into the next high part of the cycle. When the sun is not very active, the atmosphere contracts, which means there's less drag. When the sun is fairly active, the atmosphere expands, which means there's more drag. So we've been going through a period of relatively low drag. We're starting to enter a period of relatively high drag over the next 6 to 8 years. In addition, when UV light hits oxygen molecules in the upper atmosphere, they break apart into atomic oxygen, so individual atoms of oxygen, which are very reactive. You know, oxygen by itself, as you know, is very reactive. That's why things rust. But when I have atomic oxygen, it's even more reactive, and that can cause damage to the surface of your satellite. So these are issues of simply the atmosphere. Again, generally issues below about 600 kilometers. The International Space Station is at 400 kilometers, so yeah, it has to worry about this stuff. If we didn't do anything to the International Space Station, at solar maximum, the International Space Station would re-enter in about 3 months. At solar minimum, which is where we've been, it'll re-enter in a couple of years. But it's a big difference between maximum and minimum in terms of how that impacts drag. But for the most part, space sucks. We're in a vacuum. Right? And because we're in a vacuum, we have other things to worry about. One of the things we have to worry about is called outgassing. So if you have a soda bottle and you shake up the soda bottle and open up the top, you're going to hear the fizz. Well, what's happening? You're releasing pressure and the gas is escaping. Right? So the dissolved gas in the liquid is escaping because of the released pressure. Same thing can happen in space with materials. So if I have polymers or adhesives or anything like that, they tend to, during manufacturing, they'll have alcohols and other volatiles that'll get stored in there. When I release the pressure, those things will come off. We call that outgassing. And in space, there's one really important law that governs everything we do, and that's called Murphy's Law. If you're from England, it's called Sod's Law. And don't ask me why they're different, but the laws are different. The guy's different. The law's the same. And Murphy's or Sod's Law says that anything that can happen will happen at the worst possible time. And the corollary to that in space for outgassing is that outgassing will go wherever you don't want it to go, which is probably on the surface of your mirror or sensor or things like that. We also worry about off-gassing inside where the crew lives, because the crew has to smell everything. You know, if you ever bought a new car, then a car smells like a new car. Well, what's new car smell? It's outgassing plastic, right? Now in your car, you can simply roll down the window and you don't have to smell it anymore. But if I'm the International Space Station and I have a smell like that, I can't roll down the window, right? That's not gonna work for me. So that becomes a hazard for astronauts. So they wanna make sure they don't have anything smelly like that, anything that'll off-gas, plastics or things like that. We can also get cold welding in a vacuum. This is where two pieces of metal can literally get fused together because we get a weak molecular bond between the two pieces. We can get tin whiskers that can form on tin solder, which is why we like to have a bit of lead in the solder so we don't do that in space, because that crystallization can cause a failure of solder joints. And probably the most problematic thing for being in a vacuum in space has to do with heat transfer. There are 3 ways to move heat: convection, conduction, radiation. In convection is what's keeping you cool here in your room, air blowing around you. Conduction, if you feel when you stir your coffee with a metal spoon. And then radiation is what you feel when you actually feel the heat coming off a fire. Well, in a vacuum, I can't conduct anything. I don't have any air blowing around me. So the only way heat's getting in and the only way heat's getting out of my satellite is through radiation. So you see on the right there, the bottom right, you see the radiator panels on the International Space Station. So they use ammonia loops. So the ammonia flows around where the astronauts live, carries the heat, goes through those panels where it is radiated into space, and then it cools off the ammonia, and then the ammonia does another trip back through where the astronauts live. So we do testing in space using these chambers you see at the top, a thermal vacuum chamber, to make sure we know how things will behave, spacecraft will behave when we get up there into space. So that thing on the front of your car that cools your engine, what's that called? What do you call that thing in the front of your engine that cools your engine?
Radiator.
Radiator. How does it cool your engine?
Heat transfer.
Yeah, convective heat transfer, not radiative heat transfer. That thing should be called a convector. I'm on a campaign to change its name because I'm tired of people calling it a radiator. It's a convector, right? You're pumping fluid around the engine block, and then air blows over the vanes and cools the fluid. That is not radiation. That is convection, my friend. So next time you go make sure you buy the convector fluid, not the radiator fluid. It's a little more expensive, but it's more precise. So anyway, so that's an issue with being in a vacuum. Another issue being in space is all the junk. So here's the history of the junk.
Like those CubeSats?
Okay, it's important to note that each of those little blobs are not to scale, so we're up to 20,000 objects in space that we're currently tracking. So this is the box score. This comes out quarterly, so this is the last one that came out. So we're just over 20,000 objects. Nancy, that's from AGI. I think I got that off of YouTube. You could Google it. They may even have a newer one. They put a new one out every once in a while because you notice that one's about 4 years old. But 20,000 objects that are 10 centimeters or bigger. So think softball size or bigger. And that's a limit of what we're able to track. So we have tracking capabilities on the ground. So the U.S. Space Force now in charge of keeping track of that. They have the satellite space surveillance network of ground systems that track that, radar systems. And currently the limit is about 10 centimeters in low Earth orbit and about beach ball size out at geostationary orbit. That capability is about ready to change. The Space Force is about ready to bring operational a thing called the space fence, which means they'll be able to track things smaller. How much smaller depends. But people are saying what's going to happen is that number is going to change by a lot, maybe by an order of magnitude. Just because we'll be able to see things that now we know we're sure are there, but we can't see them. So now we are blissfully ignorant, but then we'll be able to start seeing them and we can't be blissfully ignorant anymore. So now instead of 20,000 objects to see, we'll have 200,000 or more that we'll have to keep track of. And that just keeps continuing to proliferate. There have been numerous satellites damaged by debris, and numerous other satellites, maneuvering to avoid debris has become fairly routine. But every time I have to move my satellite, I'm spending propellant that I'm never going to get back. So that's it's interesting. You look at geostationary. We once worked out what propellant is worth at geostationary orbit, because a geostationary satellite makes like $100 million a year revenue. If you work out what the propellant is worth per gram, it's more expensive than plutonium. It's way more expensive than gold. It's like more expensive than plutonium. So if I have to spend some of those precious grams of propellant, I'm not going to be happy if I'm going to have to dodge a piece of junk. You know what I'm saying? But that's the situation that we're dealing with. But the big dog in space is the sun. So the sun is putting out a number of things we have to pay attention to. First of all is electromagnetic radiation. So the physicists, they use this word radiation and they're not always clear about what they mean. So I'm going to distinguish between electromagnetic radiation and ionizing radiation, AKA charged particles. So for electromagnetic radiation, we mean light and heat, right? And all across the electromagnetic spectrum, literally from X-rays and gamma rays all the way up to radio waves. You can see the graph up there of the output of the sun. Most of the sun's output of EM, not too amazingly, is right in the middle of the visible. And that's a function of Wien's law, it turns out. And you see this is actually Planck's law plotted there. But the peak of that curve is right in the middle of the visible, which is convenient for us because that's what we can see. But the range is all the way from X-rays all the way up to radio waves. So that the infrared, of course, is going to cause heating. The light we can turn into solar energy. Ultraviolet can cause damage of our surfaces. We can get radio interference from the sun. The sun is actually very noisy from a radio standpoint. And we actually get solar pressure. We can get force from the sun, from light. So light is made up of waves or particles, depending on what mood you happen to be in when you do the experiment. And if it's a particle, we call that a photon. Now, photons do not have mass. Turns out they don't have volume either. But they do have momentum. So and that's a quantum thing. So a photon can actually transfer momentum to you. And it's not much, it's like 5 newtons per square kilometer. But if I have big old solar rays hanging out from my satellite, that can be significant over time. And if I had a really big sail, I could literally sail around the solar system, harnessing the pressure of light as I did that. So I have to worry about that. But probably the bigger worry are the charged particles. So by charged particle, I have to go back to the definition of an atom. If you guys remember the Bohr model of an atom, where in the nucleus you have a proton and electron, proton being positive, and then the electron being negative, going around the outside there, and the neutron neutral. And you probably know the story about the two atoms. Two atoms were walking down the road, one fell down, and his buddy helped him back up and said, "Are you sure?" Or he said, "Are you okay?" He says, "No, I think I lost an electron." He said, "Are you sure?" He said, "Yeah, I'm positive." So that's how you know you lost an electron. And a neutron walked into a bar, and the bartender said, "For you, no charge." Bartender said, "We don't serve faster than light particles in here." A tachyon walked into a bar. So think about that one. So I got these charged particles. So I have ions, which are positive, positively charged, and then I have electrons, or negative. And they're coming from the solar wind, which I said is this constant breeze coming off the sun. And then occasionally I get these big solar particle events, which is like a gust of these charged particles. I also get them coming from outside the solar system. We call those galactic cosmic rays. And then I get them concentrated in the Van Allen radiation belts in the Earth's magnetic field. So I kind of can't escape these things. And if you're watching that video on the bottom, you're seeing the sensors on the SOHO satellite sort of fizzed out there when it got hit by a big solar particle event. So it affected the sensor there. So these charged particles come in kind of two flavors, but we're going to worry about low energy and the high energy stuff. And the low energy we'll call plasma. So the plasma effects having to do with arcing, the plasma effects are mainly going to be on the surface. So arcing, electrostatic discharge, electromagnetic interference, and reattracting of contaminants. Mostly this is going to be a problem at GEO, less so at LEO, and mainly on the surface. So this is an annoyance, but not something that's going to really be a big problem. I just noticed Pete's question there, can an entire orbit be taken out with debris? We're almost there, where you see that there were some popular orbits there. Geostationary, you actually see a ring. And then in low Earth orbit, especially the sun synchronous orbits, they're getting so popular that there's a lot of debris built up there. Not to the point that that orbit is unusable, but there's certainly more debris in some orbits than others, that's for sure. So thanks for that question, Pete. Probably the most problematic issue has to do with the high energy charged particles. And so every once in a while, the sun burps out a big bunch of charged particles in a coronal mass ejection, shown in this animation in the upper right there. Luckily, most of the time it's not aimed at us, but if it is, we got to be ready. So we get this big coronal mass ejection, all these big gusts of charged particles. Lucky for us, we have our shields up. So our Earth's magnetic field protects us from that big blob of charged particles, deflecting most of it. But some of those charged particles get trapped within the field lines, and then they go down and interact at the field generators where the Klingons always target down there, and interact at the poles where the field lines come together and cause excitation of the atmosphere, which causes the glow, which is the northern lights and the southern lights. Now for our spacecraft, those charged particles are going, those high energy ones are going to go whipping through the surface of our satellite like it's not even there, and go right through our electronics. And if it happens to hit the right spot, if the little bullet happens to be in the wrong place at the wrong time, then it can cause a latch up of one of the transistors on your microprocessor. It can affect the ability for your semiconductor to carry charge. And all of that can have problems in terms of how your system's going to behave. So there's immediate effects here we call single event phenomenon, and they happen like that. I mean, and they're like little bullets going in all the time that are causing issues with how our system is going to behave. It can flip a bit, it can latch up a part of a transistor. And there's sort of two effects here. I think of them in terms of sunburn and skin cancer. So the sunburn's happening today, skin cancer is happening over many years. So you get an immediate effect, and then you get we call a total dose effect of a cumulative degradation of the ability for our semiconductor to actually work. So at some point, it simply stops working, after some number of months or years, depending on the substrate material and depending on the orbit that I'm in. That total dose then eventually causes my system to simply shut down, stop working. So, and we can look for materials that are less susceptible, but eventually everything succumbs. We have not found a system that's 100%, unless you go back to iron core memory, anything that's a semiconductor is eventually going to succumb, at least as far as the technology we know now. So we can use some shielding. People usually guess lead is the best shielding, but it turns out that's not the best. Turns out hydrogen is the best shielding. The hydrogen is not very convenient. Water would be next best, and if I have humans on board, I probably have water anyway, so that's good. On the International Space Station, they actually use polyethylene, high density polyethylene, a couple of inches of that. The polyethylene is a hydrocarbon, so there's a lot of hydrogen there. It's the hydrogen that acts as the shield for them. But whatever I do, I have to build in error detection and correction, because this stuff is going to happen. I mean, it's just price of doing business in space. So I have to have quite a bit of software overhead to be constantly checking for these problems, because they're just going to happen. So the natural environment's bad enough. Now I got to worry about the unnatural environment, the human environment. And these were the good old days. The good old days, we just launched satellites and we talked to them, and everybody was cool and everybody was nice to each other, and we didn't have to worry, and we barely had any software anyway, so it didn't matter. And that life was good. That ain't the way it is anymore, right? Now we have bad actors. We're way more dependent on software, and these bad actors are doing things like spoofing and eavesdropping and denials of service. All of these are things that we now have to be concerned about. But we're not really prepared in the space industry. So we have some challenges in our industry. First of all, as we've just seen, some of the problems that can happen in spacecraft are hard to distinguish between a natural problem and an unnatural problem. If I have a single event upset, it may not immediately be obvious that that's, because of the natural environment or because somebody hacked me. Also, space has suffered from a bit of, it can't happen here mentality, where you tend to think we're, nobody's going to bug us, but, we're special. But of course, we're not that special. And space has tended to be fairly conservative, inflexible, and very non-agile in terms of adapting over time. A bit complacent, we could say. And we've tended to view security as more of an afterthought than a forethought. And part of it is because fixing things is difficult. And we can patch our systems, we can even do new software updates, but we're limited. We can't change our hardware, and we're limited in the ability of what we can do even to our software. So we just can't react that fast. The other issue is that the attack surface just keeps growing. We're relying more and more on software. We have more and more distributed missions. We have a lot more actors involved. We have our software tends to be more outdated because we in the space business tend to build missions that last sometimes for decades, and so we're still using software from that nobody else has even heard of. And then we have trouble removing that software at end of life kind of problems. So that's the space environment issues. Again, space isn't that far away. We have a number of natural environment things we have to contend with. Big one from a upsetting spacecraft standpoint are the high energy charged particles, which will cause those single event upsets and bit flips and things. And from a cyber's perspective, what I want you to take away here that first of all, again, space is hard and space sucks because it's vacuum. So it's hard enough to get things to work in space, even on a good day, because that natural environment is a pretty big threat, and it's causing denial of service randomly already, without any human intervention. And some of those anomalies that could occur if there was a nefarious actor, we'd have a hard time immediately discerning the difference between the natural attack and an unnatural attack. And the other thing to take away is just how fragile spacecraft are. A relatively minor hack, like causing a solar array not to point quite at the sun, even if it was off by a few degrees, would decrease the amount of power it could produce, which might decrease its ability to do its mission, and on any number of things from a relatively smart area. So Gretchen's asking a question here. In the vein of threats, human actions, there are so many vulnerabilities to ground system that support space that can be attacked. What would cybersecurity hack look like in the ground infrastructure? What would they get, and how could you protect against it? We're going to tackle some more of that here in a minute, Gretchen. Thanks for that question. But as we saw in that previous section, I listed 9 different activities for mission operations, and any one of those activities is a potential inroads for an attack. And in terms of that, and because they all represent parts of the ground infrastructure as well, and some of them more vulnerable than others, but any one of those are potential inroads, because you have people, processes, and things involved, and people can be a weak area there, and sometimes just the infrastructure we have, because it's maybe antiquated or doesn't have the, and we're running, legacy software from decades ago, we have more vulnerabilities in that respect. So hopefully that answered your question. So let's check in. Any other questions from that section before I pop up the poll? So who still wants to be an astronaut after seeing the threats? Who's changed their mind? Oh, Pete, you're still ready to go. Okay. Wear your lead underwear. Oh, wait, I guess you better wear your hydrogen underwear. Take a visit over an extended stay. Kilt. Okay. Yeah, that'll help you. So astronauts will tell you, because we didn't really talk about human issues, but I mean, it gets scary to talk about what happens to humans, especially in a free fall environment. That can be pretty bad. The astronauts will tell you they'll see flashes of light in their eyes. So a charged particle goes through the eyeball, releases a photon. Your retina can detect a single photon, and they see these little light bulbs going off in their eyes at random times, which is a bit of a freak out. So that's an issue. We talked about shielding. Again, for human missions, we can use water. In fact, NASA talks about creating like a storm shelter, because these big solar particle events luckily don't last that long, days. So if you can get astronauts to hunker down underneath bags of water for a couple of days, they'd probably be okay. But the radiation effects on humans is pretty critical to look at, because a round trip mission to Mars is a lifetime dosage. NASA sets the dosage limits based on age and gender. Women can take less dosage than men, and older people can take more dosage than younger people. So of course the answer for going to Mars is to send old men, because you won't miss us anyway. And then you could argue about whether you should even bring us back. So in terms of a safety issue, but there you go. Yeah, and so Terry's talking. Terry, you want to say something about that JPL thing?
Yeah, sure. So a couple of years ago, JPL was hacked, and they were hacked because there was an unattended, unauthorized little Raspberry Pi, just a simple little computer, hooked up to their network. And so an external threat actor got in, actually came in through that Raspberry Pi or targeted it, was able to crawl around their network for about 10 months and received about 500 meg of data about one of the Mars missions. So that's just an example where, you know, you've really got to watch the people in your network and what they are putting on your network.
Yeah, and I guess be conscious that, you know, all it takes is one slip up and somebody's just waiting for that slip up, you know, in that case. You talk about gravity effects on humans. So quickly, there's three things with gravity effects on humans: moans, groans, and stones. So the moans come from vestibular issues, where you just are space sick and you feel like crap because you're just, you know, motion sick. Bones comes from a lack of force on your bones, so your bones lose mass, and then stones come from a fluid shift, because you get fluid that moves to your upper body, because your legs keep pushing fluid into your upper body even though it doesn't need to, and you start offloading liquid, which means you become dehydrated, which can lead to kidney stones. So all that are issues with gravitational effects. Building rotating space stations would be cool, but you look at the mass of the entire International Space Station, you'd need a couple times more of that mass to build something even close to big enough to be useful. Because if it's a relatively small radius, people would just throw up if they're going around in circles like that. So you need a pretty big radius, and I can't remember what the minimum radius is. Somebody's studied that, but it's like 50 meters or at least. Otherwise, the Coriolis would give you all kinds of vestibular issues. So it needs to be a pretty big thing. So now we're not quite ready to build something that big yet. That'd be nice though. All right, let me release the poll. Release the hounds. Release the poll. So we just did threats. So let's go ahead and take this poll, and then we'll give you about 5 minutes or so to take the poll, and then we'll review that. We got time for a little stretch break, and then we'll start back up at the bottom of the hour. So that should be 4:30 Pacific time. And all right, yeah. And then so I guess am I a little ahead of schedule? Maybe a little ahead of schedule. So we'll start back up at 4:30 Pacific time, and then we'll pick up with vulnerabilities here in a minute. So go ahead and take the poll, and then we'll check in and see how everybody did with that. All right, let's see how we did here. So we have a poll, show the results. So first question, space is incredibly, amazingly, ridiculously far, far away. Nope, pretty close, right? 100 kilometers. Drag affects all satellites in every orbit. Guys, I guess you missed that one. So no, right? Remember we said 600 kilometers was kind of the rule of thumb there. So if we're above 600, then no, I don't need to worry about drag. Below 600, then yeah, I do need to worry about drag. So maybe I misspoke there and confused you on that one. So I said, yeah, there's atmosphere all the way out to the moon, but not enough to worry about. But the 600 kilometers is sort of the line in the sand there for us. So those bit flips are caused by the high energy charged particles. Everybody pretty much got that one. And yeah, the scary thing here is anomalous behavior by satellite could be indistinguishable from a natural threat. So it's really hard to know right at first. And then all of the above then represent the cybersecurity challenges that we talked about. And then the key things there for denial of service was the TOS flood, the Internet of Things botnet attack, and then ping flood type issues. So most of you did okay on there. All right, so let me stop sharing that. So let's move to our last section, and then you want to stay tuned because we're going to have our little security challenge, cybersecurity challenge here at the end to see how you do. So here we want to look at some specific areas of vulnerability, the RF systems and data handling systems. So we're going to look at those pipes and those uplink and downlink pipes that we talked about. We want to know how do those pipes work? How do I set up a pipe? And that means how do I maybe disrupt a pipe as well? So these pipes are fine-tuned things. You need to make sure that they work correctly because it's all about moving the data. And then we'll look at the data handling system. So I've got my little cartoon there of a computer, and we've got some ones and zeros there. If you stare carefully there, you see that my artist put a 2 in there. So I guess that's a bit flip, and that happened. So let's start with a communication system. So this is the ears and the mouth of our spacecraft. So we have to listen for commands coming up from the ground, and we have to talk to send telemetry down to the ground. Along the way, we have to turn that data into modulated information that goes on to the carrier, as we'll talk about. So we have modulators and demodulators that work with that carrier signal that we'll look at to actually move that data from where it needs to go. And then that data then connects up to the data handling system, as we'll see here in a little bit. So the key part here is these communication architectures. So I hope that again, it's all about moving the data. So I have ground systems all over the place. I showed you those Air Force Satellite Control Network and Deep Space Network and that, Universal Space Network. We have these ground stations all over the darn place, and we're moving data all over between them. Now, space to space and ground to space, the downlinks are going to be RF. Now, once it's on the ground, then we can move things around through fiber. Right? Fiber is actually a lot better than RF for a whole lot of reasons. But for space, ain't no fiber up to space, at least yet, until we can build that space elevator. We're kind of stuck with RF links. And so that they create their own challenges and vulnerabilities, as we're going to see. So let's talk about how RF communication works, which means we have to talk about how communication works. And I'm sure everybody, when they were a kid, got to play with 2 cans and a string. And kind of unlike the cartoon in the top, the string needs to be tight. So our scientists there are not holding the string tight the way they need to, but for artistic license there. So the guy on the right is going to talk into his cup, and his voice is going to bounce on the bottom of the can, and his voice will then get modulated onto the string. Now the string is going to carry that vibration to the other person who's got the cup up to her ear, and it's going to bounce on the bottom of her cup where it'll be demodulated, and then she's going to hear kind of whatever it was that he said. Okay, so RF communication, the only difference is no string. In fact, it's the carrier that acts as the string. Right? The carrier is where we're going to modulate our information onto. But we have to have that carrier. So we have to have that string that goes from me to you, and that's how we're going to get our information there. Now, it turns out there's various ways to modulate that information onto the carrier. And in the space business, we tend to use digital communication. And there's 3 basic ways you can think of to do modulation, 2 of which you have in your car: amplitude modulation and frequency modulation. So our cartoon there shows a simple example of amplitude modulation, where low amplitude means a 0 and higher amplitude means a 1. I could do frequency modulation, so every time I shifted frequency, that could be a 0 or a 1. In the space business, we tend to use phase modulation, where every time we swap phase, we can go between a 0 and a 1. So, kind of pick your language, really. It turns out that phase modulation is a little more forgiving, so we tend to use that more in space. But we could use the others if we wanted to. We just don't. They don't work as well. But for for your car, it's fine. Works fine. So various ways to do that. Now, what we're trying to make sure happens is that we can have a conversation, right? Between the spacecraft and the ground, they need to have a conversation. And that conversation is no different from the conversation you want to have with your buddies when you're out, out at the restaurant or the bar at night, back when we could go to restaurants and bars. But I'm sure most of you remember being in a bar at one time in your life, and you're trying to have a conversation with somebody on the other side. And there's a lot of things that are going to that complicate that. First of all, you and whoever you're talking to is helpful if you're speaking the same language, right? If you're trying to speak to someone in a language they don't understand, it doesn't matter how loud you talk. Well, of course, Americans know that if you talk English loud enough anywhere on Earth, people will understand you, but that's not usually the case. So we need to make sure we pick the right language, and we also need to be on the right frequency. So if I'm using dog whistle frequency, you're not going to hear me, right? So let's pick with audio frequencies here. Distance is important. If I'm too far away, you can't hear me. And data rate is important. If I talk too quickly, you can't really understand me. You might hear me, but you won't really understand me. So I have those things to play with: language, frequency, distance, data rate, and then environment. So if somebody's making a lot of noise, then I'm not going to be able to hear what the other person's saying either. So all those things have to be balanced to make sure we have effective communication. And what we're really after here is making sure that the signal is greater than the noise. If the signal is higher than the noise, then you're probably going to hear me. If the noise is greater than the signal, then you're probably not going to hear me. And this gets tied up into what we call Fry's equation, which is for how we calculate link budgets on all of these various links I just showed you. So it looks like a little complicated equation, but it's really not that bad, because what it's really doing is implementing the things that we just talked about. So instead of being in a bar having a conversation, now I'm having a conversation between two dishes, as we show there on the bottom right. And so the same things apply. I have to pick the right frequency, in this case, the frequency of our carrier wave. I have to pick the right language, which is the modulation. I'm worried about distance, which we call space loss. I'm worried about the data rate, and I'm worried about noise. So all of those are things I have to consider, and they're all packed into that equation there at the top. Because what we're trying to do is ensure that for every bit, the energy is greater than the noise. So we call that energy per bit to noise ratio, or EB over NO. So the energy per bit to noise ratio wants to be greater than 1. And that's going to be determined by a number of things. I have only a number of things I can play with. Transmitter power, basically how loud I'm going to talk. Transmitter gain, how I maybe direct what I say. The space loss, how close I am. The receiver antenna gain, how big the ears are on the ground. And the data rate. The lower the data rate, the easier it is to get the message through. So there's not that many knobs I can turn here, but these are the things that I have to have all in place to make sure I have effective communication. So if I were to impact any one of these in some negative way, I'm going to reduce my ability to communicate significantly. And we see that already with things like Voyager. So Voyager's keeps going and going and going. Energizer Bunny, right? Eventually, the power on its radioisotope thermoelectric generator is going to give out, I think, in about 20 years, they said. But even now, it's so far away, the space losses are basically killing our ability to hear it. In fact, I don't think we're going to be able to hear it in about another 5 or 10 years. Already, its signal is below the noise, and it has to keep repeating itself over and over and over before we can finally pick the signal out of the noise. But for something in low Earth orbit, we can't have it just keep repeating itself. We want to hear it the first time if we can. So these are challenges that we have to face. And the other challenges have to do with the limitations that we have for building up these links. We have some physical limits that have to do with the atmosphere. So certain frequencies are going to get attenuated by the atmosphere, especially some of the higher frequencies that don't like going through rain very well. There's some technical limits in terms of just how big of an antenna you can put on a satellite. About the biggest antennas flying right now are about 15 meters. It's just hard to put in, and that has to fold up like an origami and then unfold. The Galileo spacecraft we show there in the illustration at the top, it went to Jupiter back in the 90s. And it had this high gain antenna that was supposed to unfurl like an umbrella, but two of the ribs got stuck together. They think it was cold welding. So they could never unfurl that high gain antenna. So they had to run the whole mission on the low gain antenna, which they lost something like an order or 2 orders of magnitude less data rate to be able to run the mission, which is problematic. So, you know, just by affecting that one thing, you've impacted the mission greatly in terms of its ability to move data. And of course, there's other technical limits to consider as well. I can only generate so much power on board. And a lot of the stuff, you know, on the ground are already built. The frequencies are already established. So there's just limits to what I can do. And then of course, there's legal limits. You can't just, you know, wake up tomorrow and decide you're going to start your own radio station. The FCC is going to come shut you down. And the same goes in space. You can't simply launch a satellite and start broadcasting willy-nilly in whatever frequency you want. You have to get approval to use that. And the approval comes through the International Telecommunications Union. And that's fairly highly regulated, which is a good thing. Otherwise, it'd be chaos up there. So even though you might want to do certain things, if you don't have the frequency allocation, then you're going to be out of luck in terms of what you can actually do. So the trade space then here ends up being, you know, what can I do to affect my EB over NO? How can I make sure that when I talk, people can hear me and understand me? Well, what can I do? Well, I can talk louder, right? I can get more power out of my spacecraft, but there's going to be a limit, right? There's only so much power I have available from my solar panels. I can get a bigger megaphone, right? But again, I can only put so big of an antenna on my spacecraft. I can try to get closer, but hey, if I'm Voyager, I'm leaving the solar system, man. That's not an option. I can try to get bigger ears on the ground, but most of our ground stations are already fixed. They represent billions of dollars of investment. I'm probably not going to simply go build new ones necessarily. I can try to talk slower. That'll make it easier, but then I'm going to take longer to get the same information to the ground. That means it's going to take more passes to do that. I can try to reduce the noise in the environment, but there's a limit to what I can do there, especially for existing systems. And I can try to move to higher frequencies, but you know that means new technologies often. We're getting a crowding right now because a lot of the frequencies that space has traditionally used are starting to get more terrestrial applications as well. And when there's a contest between space application and terrestrial applications, terrestrial tends to win, which means space is getting crowded out of its traditional S-band, C-band frequencies. In fact, there's a slew of satellite orders just came in this year to try, because they're trying to provide better utilization for some of the C-band frequencies that are available, which is a good news to people building satellites. So there's a push to move space to higher frequencies, which is good for a lot of reasons, but bad because we don't necessarily have all the infrastructure in place. So it's going to represent a big investment to start moving your frequencies around. So those are issues we have to think about when it comes to these things. So those are the key issues with communication. So again, I wanted you to understand fundamentally how communication works. That, you know, we got the two cans in the string, we got our carrier, and here we have our carrier wave, which is some, you know, frequency that's been allocated to us, and then we're going to modulate our information on top of that. When we talk, we want people to hear us, which means we need the energy per bit to be greater than the noise. So that means I only have so many things I can play with there in terms of how loud I talk, how big my antenna is, distance, frequency, language, speed, environment. And then we have some limitations we have to deal with: physical, technical, legal, and a number of trade-offs then that impact what we can and can't do with that. Any questions on RF? So you just got about a semester course on RF communication in 15 minutes or so, but want to make sure you understand where because it's fairly technical, but it's a technical because it really impacts what you can and can't do. A lot of it's physics and technology, so we have to be aware of what those limitations are, both from a security standpoint and a vulnerability standpoint. Any questions on any of that? How's my EB over NO coming through? So far, so good. Nancy, can you hear me? All good?
All good.
Loud and clear.
Everything
All
sounds
right.
great so far, yeah.
Should we say 3dB? That would be good. All right. Well, let's look then at what's happening in the data handling system. So the data handling system now is really our brains of our spacecraft. So it's doing all the thinking for us. And so it's got a lot to do, right? If you think of its to-do list, it's a long to-do list. It's got to respond to commands from the ground. It's got to come up with telemetry from the health and status as well as the payload. It's got to boot up on its own and self-test, and it has to fix errors if it finds them. And it has to control everything on the satellite. It has to control the heat, it has to control the power, it has to control the pointing, it has to control the rockets. All that stuff has to happen in board that. And it has to be ready to be updated. So over-the-air updates, kind of like a Tesla, it's going to be ready for over-the-air updates whenever they're ready. And that could be patches, it could be complete software updates over the life of the mission. So that's a lot. On top of that, it's got to do it in the space environment. When we just talked about how nasty that place is, so I have to deal with all that on top of everything else. So it makes this data handling problem pretty difficult. So that brains of the operation then is tightly coupled to the communication system, because it doesn't do me any good to handle data if I can't communicate it. So sometimes it'll be called the command and data handling system, sometimes the communication and data handling system. Depends on who you talk to and which organization they're in. But it's all about moving the data, right? So I can't communicate the data if I can't handle it. And just because I handle it, I still need to communicate it. So all pretty much goes together. So what's in there? So let's look under the hood here and see what's there. And not too surprisingly, we're basically talking about a computer, right? So what's in there? Well, we've got some sort of central processing unit, probably multiple central processing units. We have memory, RAM and ROM, pretty much, solid state memory these days. You don't fly tape drives anymore. And then input-output devices. So space business tends to lean heavily on standards. So there are a number of data bus standards that are fairly common. One is called MIL Standard 1553. There's another one called SpaceWire. And they'll, the 1553, I want to say is about 1 to 3 megabits or something like that data rate, which is fine for most applications on a satellite, and people build equipment to that standard, so it's easy to get to. And then we have a lot of other components too. So we have transducers that are measuring stuff all over our spacecraft. So whether it's temperature or pressure or whatever, we have transducers that act as analog to digital converters to turn those analog world into a digital world so that we can do stuff with it. We make a lot of use on space systems on field programmable gate arrays, FPGAs. They're fairly versatile processor units that you can program in firmware to do any number of things. We'll use them for digital signal processing and other kind of well-defined tasks on board a spacecraft. So you'll see a lot of FPGAs show up. And then sometimes application-specific integrated circuits that may be a custom circuit that are done for a specific application. Again, maybe digital signal processing, or maybe some particular payload interaction or something that we're doing. That's all the hardware. Of course, the hardware is kind of the easy bit. And then we get to the software, right? And without software, we got nothing, right? We just got a box of silicon. So it's a software that's enabling. So we more and more think of spacecraft as a box that flies software. We think of software as the complexity sponge for how everything gets done. As you go around the spacecraft and look at every single subsystem, pretty much every subsystem needs some amount of software, some more than others, but it's pretty hard to do much of anything without software. And software, and that's true across aerospace. There was a gentleman giving a talk a number of years ago from Lockheed Martin. I think he was a chief technology officer, chief scientist, and he was talking about that. I think he was talking about the F-22, and he said that the half the cost of the F-22 was in testing, and half of that was in software. And he made the kind of the joke, and he said he was only half joking, that Lockheed might be better off giving away airplanes and charging for software. And that's kind of where we're going, right? The price of hardware is asymptoting to zero, and the price of software is asymptoting to infinity. So most of the cost these days is in software development, testing, maintenance. We're kind of shifting to a world of DevOps, of where we're kind of continuously maintaining and developing your code, because that's where the functionality is. I mean, and I'm a hardware guy saying this and having to admit how important software is. So this is where we're going, and we're depending on it more and more. So software use has been going up following Augustine's law, which is 10x every 10 years or so. It's funny, you go back to 1960s and NASA flew Mariner 6, I think it went to Venus, with 30 lines of code, 30 lines of code. Now it's probably machine code, and all of you who do software know that lines of code is a terrible metric, but we use it anyway, because if you can't measure what's important, measure what you can and argue that it's important. But we, so now fast forward today, and when they launched the rover on its way to Mars last week, it probably had something like 2 million lines of code on it. 2 million lines of code is not impressive when you compare it to a car. So a new car probably has 100 million lines of code. But space is different, right? So we're, even so, space is going up exponentially in its use of code, and the way we use code is still different from a car, where we have a lot more demands on space software than we have even on automotive software, and that creates, again, more of a threat space for us to be concerned about. And when we start depending on code, of course, code can let us down. So this is that famous example of what happened with the Mars Climate Orbiter. And Mars Climate Orbiter was on its way to Mars, was going to enter orbit around Mars back in '99. And the way this mission was, and I'll play the video there. So it was on its way to Mars. It was going to enter orbit around Mars, and it was going to fire its rocket to enter orbit. Remember, it's on that hyperbolic trajectory, and if it was going to just fly by Mars if it didn't slow down. So it gets ready to slow down to enter orbit around Mars, but wait for it, they were only off by 169 kilometers, which means they entered the orbit atmosphere of Mars and burned up, and there they went. So all because of a units problem. This is the infamous units problem you might have heard about. So what happened here is that there were, the way this mission was operated is you had operators in Denver who were keeping track of the bus, basically, and then you had the mission control, which was at Jet Propulsion Lab out in California, who was managing the mission. The guys managing the bus out in Denver were keeping track every time the satellite fired these little rockets, and they'd use these rockets for attitude control, but they also had slight impact on the trajectory as well. And they were keeping track of all these rocket firings, and they'd put it into a file, and then they'd ship it out to JPL, where they would actually model the trajectory. Well, the guys in Denver were putting it in the file, modeling it as the thrust being in pounds force, which is an English unit, and then they shipped it out to JPL, where they assumed it was in newtons. Well, what's the difference between a pound and a newton? It's a factor of 4. And the way I tell Americans to remember this is when they go to McDonald's in Paris, because every American who goes to Paris goes to McDonald's, that they should order a Newton burger instead of a quarter pounder, because that's how you remember that. Not a true thing. They don't really sell Newton burgers, but there you go. So they were off by a factor of 4, which, again, they weren't firing these rockets very much, so it was a relatively small correction. And to me, there's an interesting Murphy's Law thing going on here. You think about it, they could have been off 160 kilometers in the other direction, right? I mean, left, right, up, down. It just happened to be down. You know, it's talk about flipping a coin and having it go the wrong way. It's simply the way it ended up. If they'd ended up 160 kilometers further away from Mars, they would have still entered orbit and they would have said, oh, wow, look, and they would have been fine. But because they flipped the coin the wrong way and they ended up closer to Mars, they burned up and all that because of, you know, the way they managed the software there. So they didn't, the software management development plan was not fully followed. And they hadn't actually, interestingly enough, they never categorized this as critical software. Pete's asking how much margin of error do they allow for? You'd think they would allow for more than that. 100, you know, they made it, you know, 40 million kilometers and we're only off by 160. So you'd think they'd have a little bit more margin for error than that, you know, because, you know, once you're, you know, if you're trying to get into a 400 kilometer orbit around Mars and you instead entered a 600 kilometer orbit, the cost to change that is relatively small. So I don't know if they were just trying to, you know, show off and see how closely they could get, but that did not work out for them. But you're spot on there on that question. Any questions about this particular debacle? There's other examples of software getting us in trouble in the space industry. There's the maiden flight of Ariane 5, where they reused software from Ariane 4 because, you know, heck, it was just a different rocket. Why not? And that reused software caused a trajectory deviation, which caused the rocket to blow up. So, so these kind of things can get us in trouble. Mars Polar Lander, basically one requirement was not allocated to software. And so you can't really blame software on that one. It was really more of a system engineering failure. But, you know, these sometimes, you know, seemingly simple things can cause total disaster on systems like this. And this is all us doing it to ourselves, right? You know, let alone some nefarious actor getting in there and helping us along, you know. So we do enough damage to ourselves without that. The lander, another lander was a European lander, Schiaparelli, which I can never pronounce correctly, but he was the guy that discovered the canals on Mars. That crashed again. That was probably not a software error, but not completely well-defined software in terms of how it handled the excursions on the inertial measurement unit. So, you know, there's always, you always kind of point to a root cause problem. But, you know, again, the space is hard enough without people doing bad things to us. All right, any other questions on that? So key design issues then to think about for data handling. You need to know what level of autonomy your spacecraft has to deal with. Again, the more autonomy, the more complexity. You have to understand all the tasks. What are you expecting your software to do and where will it get done? We have some choices. We can do things on board. We can do them on the ground. We can do it in hardware. We can do it in software. We can do it in software. We can do it in firmware. You have to understand the environment that you're going to be dealing with. How bad will that ionizing radiation environment be? NASA has a mission at Jupiter right now called Juno, and they had to take all the avionics and they put it inside a titanium vault, and they used the best possible avionics that they could get and still did all the shielding. And so far it's been holding up. They thought it would only last about an Earth year, but I think they're going on, what, 3 years? I haven't seen much report on what their single event upset issues are, but they seem to be still doing okay. But Jupiter has an even worse radiation environment than the Earth because it has a more intense magnetic field. NASA's talking about landing on one of the moons of Jupiter, Europa, where they have the ice fields, and there's the under the ice there's an ocean where the intelligent whales live. And but they think when they land on that surface on the ice there, they may be only good for a month or two because of the radiation environment there. So luckily the intelligent whales are protected by all the ice, so they're good. But I'd probably mutate a lot. What was the thing from the mutated sea bass? These are mutated whales. But, anyway, so the other thing I need to think about are developer needs, right? So I got to develop this code. How are we going to build it? What language? What development environment? What tools? How am I going to test it? And then we have all the operational abilities to consider: flexibility, maintainability, and we should also throw sustainability in there. One of the challenges we face in the space industry, especially, is that we tend to use stuff for decades. When the last space shuttle mission landed, the last HAL programmer lost their job because the shuttle was programmed using a language called HAL, circa state of the art 1975, which by 2005 was no longer a thing. So when we're trying to maintain software for decades, that creates huge problems for us, and of course threat surfaces as well. So these are the takeaways then for the data handling: understanding what it needs to do, how it has to correct for errors, the hardware-software interactions that we have to deal with, and all the software functions that have to be performed both on board and on the ground for our data handling system. So takeaways from a cyberspace lens here, that first of all, RF security is a relative small sub-niche of cybersecurity, because we tend to focus, as you might expect, more on fiber, because that's what most data is moving around. But RF is unique. We are uniquely dependent on RF in the space industry. Now, and getting access to that equipment is relatively easy, but as we mentioned, everybody tends to encrypt their stuff, so you have to know their encryption capability. But there are a lot of hardware software vendors out there. There are multiple development environments. There are legacy languages, and all those create additional vulnerabilities. And then, of course, space relies heavily on software, and the more people get involved there, the more both grounded on board, the more additional vulnerabilities we end up making. Any questions on the vulnerability section, on the RF or data handling? How are they looking at future AI? Yeah, AI is an interesting discussion. I mean, space, I'd say, is fairly far behind on that in a lot of ways, because again, we tend to be pretty conservative in how we approach that. I've seen discussion of AI more for things like data mining on going through, Kepler's data for looking for planets, using it, for post-processing, but not so much for real time. I remember even back in the 80s, there was talk about, expert systems supporting operators, but it's amazing that even 30 years later, that still has not really become a thing. So, it's a kind of that trade-off between autonomy versus automation that we get a lot. So I don't see a whole lot of talk, Terry might have a better insight there, but I haven't heard a lot of talk in the space business about more emphasis on AI certainly for operations. Decision support, yeah, maybe for operators, but again, I remember that being quite a bit of talk many years ago, but I haven't heard much recently about that. Terry, do you have an update on AI applications?
I don't, not in the space arena. I haven't really seen anything there either.
Yeah, again, we tend to be pretty slow to the party for new technologies like that. We're going to find the slides, Menno. They are posted, and maybe if Matt's on, he can tell you where they are in the Discord channel. Are they in the Discord channel, Matt, the slides?
They are in the Discord channel.
Yeah, Menno, they're there, and if you can't find them, email me, and I can always send them to you. Okay, let's pull up. I'm going to do two things here. I'm going to give you your cyber challenge. So here's your cyber challenge for the day. So I'm going to go through the challenge, then I'm going to post the poll. Then you can take the poll while you're thinking about the challenge, and then we'll get back together and talk about it. So, so here's our scenario, right? So there's a company called Wiley Imaging, and they've been operating a high-resolution commercial remote sensing satellite now for about 2 years, and the U.S. government is one of their biggest customers. It's in a sun-synchronous orbit at an altitude of 710 kilometers, and it has a node crossing of 1030 southbound every morning. Right? Or in the morning, when it crosses the equator going south, the local time is 10:30 in the morning. Okay, that's we call it sun synchronous. That means you get shadows, get mid-morning shadows every time you fly over the equator like that. Wiley operates their own ground station here in Colorado, but they lease access to 2 other ground stations in Norway and Alaska. They're up at the high latitude, and this is a sun synchronous, which means it's nearly a polar orbit, which means the Norway and the Alaska orbits, ground stations, can see that satellite nearly every orbit, which is convenient. The satellite was built by Acme Aerospace in Iowa, and there are 2 other satellites currently in development that plan to be launched next year. So that's the background. So the issue is, during the last 2 passes, we had a pass over Norway, and then we had a pass over Colorado. The operators noticed bad headers on about 10% of the health and status telemetry data packets. They didn't see any problem with the payload data packets. And it's actually not unusual that you have separate downlinks. You have a downlink for health and status, and you have a separate downlink, separate frequency for payload data. So the fact that those are different is not too amazing. It's actually kind of normal. So they only saw the problem with the health and status packets, and it's on the header on the packets. But this is about 1,000 times worse than they would have expected, because we usually plan for like 10 to the -5, 10 to the -6, let's say 1 in a million bits to have a problem. And here you're seeing about 1,000 times worse than that, or maybe even worse than 1,000 times worse. So it's a lot worse than they would have expected. So here are your challenge questions. So first of all, how would you determine if this issue were due to natural or man-made causes? What would your potential reasons be if it were natural causes? Assuming though that it's malicious cause, what opportunities would a bad actor have had? Assuming it's malicious cause, what vulnerabilities could a bad actor have exploited? And then, given there are 2 other satellites in development, what other design or operational changes could we think about to prevent future issues? So those are the questions I want you to ponder. While you're pondering that, I'm going to put up the poll, last poll of the day here. So I'll let you multitask here. So you can do the poll and then think about the cyber challenge, or you can do the cyber challenge and then come back and think about the poll. But let's take about 10 minutes to go through that. And I'll give you 10 minutes to take the poll and think about the challenge. And then we'll get back together and we'll see if some brave soul online here wants to volunteer their answer to the challenge. So if you have a multi-deck slide presentation in the next 10 minutes, I'll let you share that with the team. So let's take about 10 minutes and think about the poll questions and the challenge scenario, and then we'll bring it back together, review the poll, and then we'll step through the how to think about this particular challenge problem, and then we'll wrap it up and we'll be able to call it a day here on time. So so go do one or the other or both, and we'll check back here in about 10 minutes. If anybody has any questions about the challenge, just let me know and we can try to clarify things for you. We'll be looking for a brave volunteer who wants to tell us how to solve the challenge here. And I've also posted an end of course survey. We can't use polls for surveys because the data is not persistent in Zoom, so we're using a separate polling thing. But if you could follow the link to do that poll, we'd appreciate your feedback. That'd be great to help us figure out how to improve the course for next time. So I'll give you another 5 minutes or so to think about the polls, our poll questions here, and then we'll pull together and talk about the challenge and then wrap it up. much attendance on the polls here, but let's go ahead and close that out, and then we'll talk about our challenge. So, which of the following change would not increase EB over NO? So data rate. So making a higher data rate would be the wrong way to go if I'm trying to increase EB over NO. To jam a satellite, you need to have some noise at the receiver. That would do the trick. Threat surface software has not been static. Over the years. It's been growing. To spoof a satellite, you need to know all of the above things, which is a lot of things you'd have to be aware of, which means you probably need some sort of way to get into the details of people's design requirements. Space software is both light and agile. Actually, no, we're kind of the opposite of light and agile in the space business. All right, well, let's talk about the challenge. Do I have any brave soul online who wants to tackle the questions? Anybody feel confident about talking through how you think about these challenge questions? Only one person at a time. That's a nice thing about virtual presentations. The ability to remain anonymous is much higher. When you're in a classroom, it's sort of kind of hard to hide. You know, I can hover over you and intimidate you to tackle it. So
it's less intimidating if we talk through it together.
There we go. Let's do that. Let's kind of talk through the background first. So remember the background information here. So I just want to highlight some things that come out of the background. You know, and as we approach these, you know, as you go forward and start thinking and working in this environment, we're thinking about, you know, what kind of information should I be keying in on? So on the first bullet there, we want to key in on the fact that the U.S. government is one of their largest customers. So certainly everybody in the world is sort of fair game, but the U.S. government is sort of a high profile target. So if you're supporting the U.S. government, you're kind of putting a target on your back. So that raises the threat potential up quite a bit. Just the fact that they got government's one of their big customers. The next bullet has to do with the orbital mechanics, which we covered here within the class. So just the type of orbit I'm in will in this particular orbit will limit the number of times a day that somebody could have access to that satellite from a given site. So that really restricts when somebody could have had access to that satellite, you know, line of sight. So that is a constraint that kind of narrows the window there in which somebody could have had access. The other thing to clue in on there is that the Wiley is operating, they're leasing ground stations in Norway and Alaska. So these are leased stations. So these are companies that are basically just selling time on their ground site. So these people, anytime like I'm leasing something, I don't have a lot of control over the software, the procedures, the personnel. You know, these people are just doing a job, passing data from one person to another. They're going to work, you know, get my data right now, and 10 minutes from now, they'll get data from somebody else. They don't have any particular loyalties to me, my company, my data, my program, or anything, right? They're just doing a job. And that means I don't have a lot of insight too, because I'm basically buying by the minute. I probably can't demand to see all their software, their procedures, their security reviews, their, you know, polygraph interviews with people. If they do that, I don't have any right to ask that stuff, right? I'm just buying by the yard. And then finally, we got two other satellites in development, which is maybe a good thing. We ought to think about, okay, well, if there is a hard problem that we've come up with, maybe there's a chance to resolve that. Pete's saying, can you put that in the contract? You can try, but you know, if I'm Universal Space Network, I probably have 100 customers, and I got one small customer coming in demanding a bunch of stuff for security. I might just tell them to take a hike. Like, sorry, I don't have the time to give you that, or I'm going to charge you a lot for that. You know, so it just depends on how big of a lever you have, and you know, if you're one of end customers, you probably don't have that big of a lever on that. So the other thing then to think about from an issue standpoint, so as I said, this issue only impacted the health and status, which is not necessarily unusual. So that should not, it's not overtly suspicious. So that shouldn't necessarily raise any alarm bells, but it's a useful thing to be aware of. So it appears the problem is just in how the protocols are implemented. So this tends to be a software thing where you're going to be taking all these ones and zeros and organizing them into packets and adding headers and footers and things like that. But it appears to be random, but it only appears to be on the headers. So, but again, depending on how that packet protocol works, that is not necessarily suspicious either. But these are all things to just file away in the back of your mind before we tackle the question. So we always want to make sure we understand the lay of the land before we dive into the details of the question. So first question is, well, how do we know that if it's natural or man-made? So I put up here what's called a fishbone diagram or root cause analysis or Ishikawa diagram. Some of you may have seen these before, but they're a very useful tool to try to get at root cause. And we do it without prejudice. It's a brainstorming tool, and you can think of it as a mind map if you're used to mind maps. But so we kind of list, and you've all seen detective movies, right, where the detectives have the big board and they have the suspects and they have, yarn going between everybody in circles and all that. I mean, that's kind of what this is. This is our suspect board. And so we say, well, who are the usual suspects, right? And equipment, process, people, materials, environment, management, those tend to be the usual suspects. And we would lay out within those, okay, from an equipment standpoint, what could cause this problem? What from a process standpoint, what could cause this problem? And we're not trying to solve the problem. We're trying to say, who are the suspects in this problem? And then we can start whittling away. Once we've defined the space, might call the trade space of options, then we can start whittling away. We can go interview the suspects, see if they have an alibi. If they have an alibi, then okay, then they're not a suspect anymore. But we'd be thinking about equipment on board. Okay, well, what about that equipment? Hardware, software? Are there any processes? Maybe somebody on the ground did something wrong in the configuration, and it's being garbled on the ground. Maybe it's fine on the spacecraft. It's getting garbled somewhere on the ground. Maybe there's people. Maybe people that had poor training. Maybe there's people that are maliciously, scrambling this on their own. I don't know. Environment, of course, would be the big thing to look at. Single event upsets, and what we might do there is call up the space weather people and find out if there was any sort of large coronal mass ejection somewhere in that time period. We're trying to correlate, the time, because we can sort of narrow down when it happened, because it seemed to be fine one pass and then it wasn't fine the next pass. So that narrows down the window there. And if there was any sort of specific thing going on, maybe there was a solar event that could have happened in that time frame, or maybe it was going through this area, the Van Allen belts we call the South Atlantic anomaly. Any of those things could raise our suspicion level. You're saying, wouldn't that affect everything, not just the headers? Well, it's random, right? So all I need is one silver bullet to go into my software, and I don't know what it's going to do. And if it just happened to affect the one place where that gets encoded on the headers, then I can't immediately rule that out. It's high, low probability, but I wouldn't immediately rule that out, right? So I want to take a look at it, and I want to do this systematically. What we're trying to do is have an unbiased, let's not jump to conclusion and start launching nuclear weapons at bad guys because they attacked our satellite. We want to let's find the smoking gun, but let's do it methodically. So this is how I would go about trying to come to that root cause, and we may decide no, the probability of this being natural is just too low. It has to, and the impact is too systematic. It's not random enough, and therefore we might start to suspect people, which is malicious actors in that case. If it were environment, which is question 2, again, we've been talking, it's most likely a single event upset that could cause that, but not necessarily. It could be maybe thermal stress led to a problem with a processor or something like that. So there are other potential environmental causes as well, but single event upsets tends to be one that causes these sort of random events. But assuming it is malicious, going to question 3, where are the opportunities? Well, I mean, if it happened between passes, that's a pretty narrow opportunity. I say maybe an hour, they could have had opportunity to do something directly in there. And again, that's not out of the question, but that would mean they would have had to actually command our satellite directly, which means they would have had to know all those things we talked about. They'd have to have the frequency, they'd have to have the encryption, they'd have to have the command codes. They'd really have to know our system very well. Not out of the question, but again, fairly low likelihood. So it would seem it's probably more likely that came in somewhere sooner, and maybe it came in as a Trojan horse to be, with a time tag that says after 30 hours from now or 30 weeks from now, implement this. And so who knows when it was injected? It could have been all the way back to the factory, right? So we don't know at this point. But those are, so that's the malicious thing. That's the scary thing about code, is that you can put code in that can be sitting there, kind of the sleeper agent to get activated who knows when. So what are the vulnerabilities then? Just, again, if I'm talking about hundreds, a satellite like this probably has hundreds of thousands of lines of code. Yeah, you could be hiding in there somewhere and maybe get overlooked. Maybe you can get overlooked during testing. And the fact that we've got we're using the ground stations, that to me, that's a red flag, and that it's just, you've got things outside your span of control, your direct span of control, that can be entry points for bad actors there. And then finally, because we have these guys still in the barn being developed, if it turns out the problem is a natural environment problem, that our hardware maybe is not robust enough against single event upsets, I mean, we could consider swapping out processors. I mean, that's a pretty major design change, especially fairly late in the game. But if it turns out we're particularly vulnerable, or maybe there's some thermal issue that caused it, we may have to take a serious look at our design to see if we can mitigate that through a design change. If it's code, we may have to do a full scrub. We may have to go back through and look at all the software ground and on board to see if there's anything hiding in there. And maybe we need to go take a look at our personnel. Maybe go to do a security check on our people and see if there's anything suspicious going on there. And somebody, driving to work in a Ferrari, and last week they had a junker car, and where'd they get all the money all of a sudden, kind of thing. That might look suspicious. So those are things we could look at. Pete's asking if it was a code update, how would they consider do that for ones on orbit? Well, we actually can change code on orbit pretty well. I mean, again, depending on the extent, you couldn't change your entire architecture maybe so much, but if it turns out that was, this was lurking in one unit or module of code, we could, that would be not, I would say, easy thing to do, but it's a doable thing to overwrite that code or patch around it or something like that. Yeah, we make code changes fairly often. I mean, almost, I would say routinely are making code changes on spacecraft. So that would not be a difficult thing to do, depending on the extent. Now, again, if it's corrupted badly, that might take a lot of surgery to fix, and we may not have a choice there if this is the problem. Anybody see, did I miss anything there? Any other issues or ideas that maybe we might want to think about as we tackle this challenge? All right, well, I think we did pretty well then today. So let's recap what we did today. So we We went through, we started with context. So we looked at that mission architecture and the reasons we went to space. We talked about opportunities. So we looked at orbits and operations, got you all up to speed on how to do to become orbital mechanics. So you're getting ready to get out your wrench and fix an orbit next time. We looked at threats, natural and human threats, especially those natural threats and how insidious they can be. And just the denials of service we get on a day-to-day basis just because space is a hard place to be. And then we finished up looking at those vulnerabilities. So the RF links, spend some time looking at how we make sure that we get viable connections through the RF links. And then talked about the data architecture and overall data systems ground and on board that also become potential threat surfaces for us. So that was what we tried to cover. These were our objectives. So again, we're trying to climb that learning trajectory there from the pad all the way into orbit. Wanted you to have some core space knowledge so you feel a little more confident talking to people about space issues and some of the limitations and capabilities and threats and vulnerabilities that are out there. Wanted you to understand some of the trade-offs, especially as they apply to cybersecurity domain. Things like the access that you get from orbital mechanics and all the different things that happen in operations, those 9 different things that we laid out of activities and operations, and any one of those can be a potential entree for a threat. The natural environment, I hope you had an appreciation for how hard that environment is just on a good day. And now when we throw bad actors in there, what relatively small changes can have big impact on overall mission operations. And then finally, wanted you to be able to step back from some real world scenarios and apply the knowledge that we gained here in the class and be able to look at those critically to understand what kind of issues might come up and how would we think through these issues. And we're going to see these issues, I think, come up more and more over time. And we have to be able to differentiate the naturally occurring problems from the unnaturally occurring ones, and then figure out what to do about it. I mean, we've got there's a lot of potential holes to plug here in terms of vulnerabilities, and we may be, running around plugging holes or all our life, but we have to be able to ready to identify those holes and think about what kinds of things we can do to address them going forward. So we thank you for your time and attention. Thanks, Terry. Thanks, Jason, for this. And I'll probably stop recording at this point. And so I'll just kind of throw it open to any other questions. I'll hang around as long as anybody needs it, they have questions, and we will go